This part covers three core architectural patterns for building agents: planning, reactivity, and multi-agent coordination. Understanding these patterns helps you design agents that can reason about the future, respond to changes in real time, and collaborate with other agents. Why architecture changes what an LLM can do. Architecture as the real capability lever. A useful way to think about an LLM-based system is that the model supplies judgment, language, and pattern completion, while the surrounding architecture determines what the system is actually allowed to do with those abilities. The same model can behave like a passive text generator, a disciplined workflow step, or an autonomous agent, depending on whether it is given a control loop, state, tools, and clear stopping conditions. In that sense, architecture is not decoration around the model. It is the mechanism that turns latent language ability into operational capability. When practitioners say that a system feels smarter, they're often responding less to the model itself than to the way the model is being asked to work over time. Figure 2.1. The same LLM can behave very differently depending on architecture: a single pass generator, a workflow step, or a closed-loop agent. This distinction matters because architecture governs the sequence of decisions, the points at which evidence is incorporated, and the conditions under which the system can revise itself. A single prompt may produce a polished answer, but it cannot by itself create a second chance to inspect the environment, branch on a new observation, or ask for help before continuing. Those behaviors require an execution structure that can hold state between steps and decide what happens next. Once you introduce that structure, the model is no longer only generating content. It is participating in a control process. That process, rather than prompt length, is what creates agent-like behavior. A simple control systems analogy makes the point concrete. A one-shot LLM is like an open-loop controller. It issues an output and moves on without checking whether the output was adequate, whether the world changed, or whether a previous assumption failed. An agent loop is closer to closed-loop control. It acts, measures the result, and uses the new measurement to decide the next move. Closed-loop systems are more powerful not because they are more verbose, but because they can correct course. In agent design, that correction ability is often the decisive difference between a system that sounds capable and one that can consistently complete a task. Figure 2.2. Open-loop systems emit outputs. Closed-loop systems observe results and correct course, which is the basis of iterative agent behavior. The architectural perspective also clarifies an easy misconception. Large prompts can simulate complexity, but they do not create new decision points. A long instruction block may tell the model to be careful, to verify, to compare options, or to consult a tool, yet the model still has only the execution opportunities the architecture grants it. If the system never pauses to observe a tool result, then no amount of prompt elaboration can make it adapt to that result. If the system never stores intermediate state, then no amount of wording can make later steps depend on earlier ones. Capability emerges when the prompt, state, and control flow work together. Why prompt quality alone hits a ceiling? There is a persistent temptation to treat prompt engineering as the universal answer to every agentic problem. The logic is understandable. If a model fails, perhaps the instruction was too vague. If it misses constraints, perhaps the prompt was not detailed enough. If it answers poorly, perhaps it needs one more paragraph of guidance. This mindset is useful up to a point, because prompts do shape the modeled behavior and can dramatically improve consistency. But prompt quality has a hard ceiling when the task itself requires revision, branching, or interaction with the outside world after the first pass. That ceiling appears because prompts influence what the model says, not what the system can subsequently know or do. If a travel assistant must compare hotel options, check weather, verify a flight connection, and then revise the plan, the missing ingredient is not more text telling the model to be thorough. The missing ingredient is a loop that lets it search, inspect the result, update its state, and continue. Without that loop, the model is forced to compress the entire task into a single response, which means it must guess, assume, or overcommit. A prompt can encourage caution. It cannot manufacture fresh evidence. Another reason prompt-centric thinking reaches a limit is that it conflates description with control. A prompt can describe a process in elegant detail, but unless the surrounding system enforces the process, the model may still skip steps or collapse them internally. This is particularly visible in tasks with meaningful side effects. An LLM can be told not to book a flight without approval, but if the architecture does not actually pause execution at the approval point, the instruction is only advisory. Architecture turns guidance into enforcement. That is why production systems care so much about state transitions, routing logic, and explicit pauses rather than just more elaborate instructions. The practical pitfall is that prompt inflation often feels like progress. Longer prompts create a visible artifact, and visible artifacts are psychologically reassuring. There's clearly more context, more specificity, more caution. Yet the system may still be fundamentally single-pass. In those cases, the user experiences a polished but brittle answer that cannot repair itself when the first guess is wrong. The architectural remedy is usually smaller and more powerful than the prompt rewrite the team was attempting. At a state transition, at an observation point, at a place to stop and reconsider. That is the point at which the system begins to behave differently, not just talk differently. Single-step execution, a useful but fundamentally static baseline. A single-step system is one that receives a task, performs its internal computation, and returns an answer without revisiting the world or its own intermediate results. Operationally, it may still use a lot of internal reasoning before producing the final output, but the work happens within one execution turn. There is no external checkpoint between subdecisions, no opportunity to observe a tool result and change direction, and no explicit stateful continuation from one decision to the next. The system may be capable, but it is still static in the sense that its behavior is fixed for the duration of that single pass. That static behavior is not a flaw. Single-step execution is often the right design for translation, classification, extraction, summarization, and other tasks where the main objective is to transform input into output within a narrow boundary. If the task is well specified and the result can be validated after the fact, the simplicity of a one-shot call is a strength. It is easier to reason about, easier to debug, cheaper to run, and less likely to wander into unnecessary complexity. In production, many valuable systems should remain single-step because the problem does not justify more autonomy. The limitation appears when the task includes uncertainty that can only be resolved by inspection. Suppose the Atlas Travel Assistant is asked for the best itinerary between two cities with multiple constraints: budget, arrival time, preferred airlines, and a narrow layover tolerance. A single-step answer can still be useful, but it must either infer the missing facts or hedge its response. It cannot search for live fares, compare competing options, notice that one flight has an impractical layover, and then revise the recommendation based on evidence. Those are all multi-step behaviors. The difference is not merely that more things happen. It is that later steps can be shaped by what earlier steps discovered. Single-step systems also struggle when the correct answer depends on branching. If one hotel is unavailable, another may fit. If the first summary omits a key policy detail, the answer should be adjusted. If the tool output contradicts the model's initial assumption, the response should change course. A single step has no natural place to make that correction, so the burden falls back onto the model to anticipate every branch in advance. That is a bad bargain when the environment is dynamic or the decision space is large. The one-shot baseline is useful precisely because it is limited. Those limits become visible as soon as the task requires adaptation. The capability jump from iteration. Iteration changes the system from a static generator into an adaptive controller. Once a model can perform a step, inspect the result, and then decide what to do next, the system gains a qualitatively new kind of capability. The new capability is not simply more tokens or more thinking. It is feedback. A step can be corrected because it was followed by observation, and observation can influence the next action because the system retained the task's current state. That feedback loop is the architectural source of agentic behavior. The practical effect of iteration is easiest to see when the first assumption is incomplete. A travel agent may begin by searching for direct flights because that is the most desirable default. If no direct flight fits the budget, the next step can relax the constraint and compare one-stop options. If a tool reveals that a connection is too risky, the agent can revise again. Each move is not a detached answer, but a response to the evidence produced by earlier moves. This is what makes iterative systems resilient. They're not trying to predict the entire problem space in one shot, because they can learn from the problem as they go. Iteration also changes how intermediate uncertainty is handled. In a one-step system, uncertainty is typically buried inside the final answer, where it becomes hard to separate confident conclusions from guesses. In a multi-step system, uncertainty can be externalized into the process. The model can mark a candidate option, test it, reject it, and continue. That creates a trace of deliberation that is operationally useful even when the internal language of the model is not exposed. The trace of steps is more important than the rhetorical style of the answer, because it tells the system where it has already looked and what changed as a result. A subtle but important point is that iteration does not merely add repetition. It adds opportunity for correction. Repetition without feedback is just redundancy. Iteration with observation is adaptation. This distinction is why agent design focuses so heavily on observe and route in addition to act. The system must not only continue, it must continue differently based on what happened. That is the essence of closed-loop behavior, and it is why architecture changes capability in a way prompt quality alone cannot. Iteration also creates a more realistic division of labor between the model and the system. The model is good at proposing interpretations, comparisons, and next actions. The architecture is good at deciding when to permit those actions, how to record their outcomes, and when to halt. When these roles are separated cleanly, the model does less pretending and more adapting. The system no longer needs to sound certain before it has evidence. It can gather evidence first, then speak with more confidence later. That is an architectural gain, not merely a stylistic one. React as the minimal reasoning action observation loop. React is the smallest useful template for thinking about agentic execution because it combines internal reasoning with external action and fresh observation. In its simplest form, the system considers the task, selects an action, executes that action through a tool, inspects the result, and then repeats if necessary. The crucial feature is not the presence of thought alone or tool use alone, but the alternation between them. React is therefore not just a prompting trick. It is an execution pattern that makes the model's next decision depend on the world it just touched. This is what makes React operationally different from a one-pass answer, even though both may involve careful reasoning. In a single-step response, the model can reason internally, but the reasoning is collapsed into one output. In React, reasoning is separated from action, and action is separated from observation. That separation matters because it gives the system a place to stop before it commits. A travel assistant can reason that two flight options look promising, act by querying a search tool, observe live results, and then route the task toward either booking, refinement, or escalation. The loop is simple, but it already contains the essential mechanics of an agent. A useful way to picture React is as a conversation between intention and evidence. The model proposes what seems plausible, the environment answers back through tool output, and the next step reconciles the two. When the evidence is weak, the model can search again. When the evidence is strong, the model can stop. When the evidence contradicts the plan, the model can revise the plan. The loop is not trying to eliminate reasoning. It is trying to make reasoning accountable to what the system actually observes. That accountability is what gives the agent practical leverage. React is also the bridge from prompt-centric experimentation to architecture-centric design. A prompt can nudge a model toward thinking before it acts. The loop enforces that thinking and action happen in the right order and that observations are not ignored. For readers new to agent systems, React is the right entry point because it is small enough to remain comprehensible while already illustrating the key idea. The system's behavior comes from how it moves through state, not from any single answer it emits. Later patterns will build on this same loop by adding explicit branching, interruption, approval, and coordination, but the core mechanism remains the same. State carried across steps, the lightest form of memory. Multi-step behavior requires something to persist across turns of the loop. That persistence is state in the narrow operational sense, the machine-readable facts the next step needs in order to decide intelligently. State might include the user's budget, the list of candidate flights already checked, the currently preferred itinerary, or the fact that human approval is pending. Without that carried forward state, each step would be forced to reconstruct the task from scratch, which would turn the loop into a series of disconnected single steps rather than a coherent process. It is important to keep this notion of states separate from long-term memory. In this chapter, state simply means the information that lets one step continue from the last. It is often ephemeral, task-specific, and tightly scoped to the current run. That is enough to make a loop adaptive. The system does not need to remember the user forever in order to compare two hotel options over 3 tool calls. It only needs to remember what it has already checked and what remains unresolved. This light form of carryover is the minimum viable ingredient for agentic continuity. Carried forward state also explains why repeated prompting is not the same as iterative execution. If you manually paste the previous answer back into a new prompt, you have recreated some surface continuity, but you have not necessarily created a stateful control loop. The earlier result may be present as text, yet the system has no structural guarantee that it will treat that text as the authoritative state of the task. In a true loop, the architecture itself knows which facts are current, which actions were taken, and which branch should follow next. That distinction becomes critical once the system must handle interruptions or multiple branches, because then the ordering and provenance of state matter as much as the content. This is where the memory analogy is useful, but must be handled carefully. Think of state as the agent's working notes rather than its long-term recollection. The working notes are what let the agent compare, refine, and continue. They're not the same thing as durable memory, which is designed for persistence across sessions and broader behavioral influence. A loop can be fully agentic with only working state. Durable memory becomes relevant later, when the system must remember across tasks or sessions. For now, the architectural point is simpler. If nothing is carried forward, nothing is being adapted. Atlas Travel Assistant, one-shot answer versus bounded planning loop. Consider the Atlas Travel Assistant asked to plan a trip from San Francisco to New York with a specific departure window, a modest budget, and a preference for minimal layover risk. In a one-shot configuration, Atlas is asked to produce the best answer immediately. It may offer a plausible itinerary, mention likely trade-offs, and present the result confidently. That output can be helpful, but it is still a guess constructed from the information already in the prompt and whatever general knowledge the model has internally. If prices have changed, if a preferred route is unavailable, or if an important constraint was missing from the prompt, the answer has no built-in mechanism to recover. Now imagine Atlas in a bounded planning loop. The first step is to interpret the request and identify the key constraints. The next step is to search live flight options. The following step compares a small number of candidates against the budget and arrival window. If the first search returns poor options, the loop can widen the search or relax a constraint. If a user's preference for a non-stop flight conflicts with cost, Atlas can surface the trade-off instead of silently deciding. Each step feeds the next, and each observation narrows the remaining uncertainty. The result is not just a better answer. It is a different kind of answer, one built from evidence gathered during execution. This difference is especially visible when the first attempt is wrong. In a one-shot system, a wrong assumption is often frozen into the final response. In the loop, a wrong assumption is just a temporary hypothesis. Atlas can search, observe that the cheapest option has a destructive layover, and revise the recommendation before presenting it. The loop gives the system room to be wrong in a productive way. It can fail early, cheaply, and reversibly, then use that failure to improve the next step. That is why bounded multi-step execution is so valuable in real workflows. The system is not merely generating text about the task. It is interacting with the task until it has enough evidence to stop. Boundedness matters here as much as iteration. Atlas is not being given unlimited freedom to explore every possibility forever. It is being given a controlled number of steps, a restricted tool set, and a defined stopping rule. Those constraints are what keep the system useful rather than chaotic. They are also what make the capability gain legible. The agent can adapt, but only inside a frame the architecture enforces. This is the practical meaning of bounded autonomy. The system is more capable than a one-shot response, but it is still governed by explicit limits. The deeper lesson from Atlas is that better architecture often changes the nature of the work, not just the quality of the output. A one-shot assistant tries to answer the question. A bounded planning loop tries to answer it with evidence. That shift has downstream consequences for reliability, safety, and user trust, which is why later sections in this chapter will spend so much time on routing, interrupts, and coordination. Once you see the travel assistant as a controlled process rather than a single completion, the rest of the chapter becomes a study in how to make that process more deliberate. Where chat, workflow, and agent diverge. These terms are often used as if they were interchangeable, but they describe different levels of control. A chat response is a single conversational turn. It may be helpful, creative, or accurate, but its scope ends when the answer is emitted. A workflow is a predefined sequence of steps with explicit transitions. It may contain branches, retries, and tool calls, but the path is largely orchestrated in advance. An agent goes one step further. It can select actions based on observations and state, not merely follow a fixed script. The distinction is subtle but foundational because it determines where autonomy actually lives. A workflow can use an LLM without being an agent. For example, a support pipeline might classify a ticket, retrieve policy content, draft a response, and then send it for review. That is a valuable system, but if each stage is predetermined and the model is simply filling slots, the behavior is workflow-driven rather than agentic. By contrast, an agent decides which tool to use next, whether to keep searching, whether to ask for clarification, and whether to stop. In other words, a workflow is about orchestration of steps. An agent is about selection among possible next steps. Chat interfaces sit at an even simpler end of the spectrum. They are excellent for open-ended dialogue and ad hoc exploration, but they do not necessarily expose the state transitions that make an agent reliable in a real task. A chat system can feel agentic if it remembers context and calls tools, but without explicit control over when those tools are used and how their outputs are incorporated, the behavior remains closer to conversational assistance than to bounded autonomy. This is why the label agent should be reserved for systems that can decide, act, and adapt through a controlled loop over state and tools. Keeping these terms separate is not academic pedantry. It prevents teams from overclaiming what a prototype can do and from under-designing the control layer needed for production. When a static workflow is called an agent, the team may expect self-correction that does not exist. When an agent is treated as though it were merely a chat prompt, the team may fail to provide the state, routing, and stopping logic it needs. Clear terminology leads to clearer architecture, and clearer architecture is what lets a system do more without becoming unpredictable. Bounded autonomy versus open-ended autonomy. The power of architecture is not that it removes constraints. It is that it lets you place the right constraints in the right places. Bounded autonomy means the system can decide within a defined envelope. It can search, compare, revise, and continue, but only until it reaches an approval point, a maximum step count, a risk threshold, or a satisfied stopping criterion. Open-ended autonomy, by contrast, allows the system to keep acting without a tightly enforced frame. That may sound more powerful in theory, but in real deployments, it is usually less desirable because it is harder to predict, test, and govern. This is why good agent architecture resembles a flight controller more than a free-roaming explorer. A flight controller is powerful precisely because it can continuously correct the aircraft's path, but it is safe because it operates within strict physical and software limits. The same logic applies to AI agents. You want the system to be able to adjust when evidence changes, yet you also want to know what it may touch, when it must stop, and who can approve sensitive actions. Capability without constraints is simply risk. Constraints without adaptability are just a workflow. The useful middle ground is bounded autonomy. From a developer's perspective, bounded autonomy also makes systems debuggable. When the architecture defines the loop, the branches, and the stop points, you can trace why the agent did what it did. You can see which observation led to which action and where the state changed. That traceability is not a side benefit. It is a prerequisite for production use. A system that can act but cannot explain its progression through state is difficult to trust. Architecture gives you a way to let the model improvise locally while keeping the global process legible. The best way to interpret bounded autonomy is therefore not as a restriction on intelligence, but as a design choice about control. The model contributes flexibility, but the architecture contributes discipline. Together, they create behavior that is stronger than a one-shot prompt and safer than an unconstrained loop. That tension between freedom and constraint is the organizing principle of the chapter, and it is why the upcoming patterns matter. There are different ways of shaping that tension for different kinds of tasks. Why this framing matters for the rest of the chapter. Once architecture is understood as the source of capability, the rest of the chapter becomes a study in control flow rather than a catalog of unrelated agent tricks. Structured reasoning will show how to organize thinking before action. Human oversight will show where to pause the loop when the consequences matter. Multi-agent coordination will show how to distribute decision-making across specialized components without losing control over the whole. These are not separate inventions, so much as refinements of the same basic idea. The shape of the loop determines the shape of the system. That framing is worth holding on to because it prevents a common error later in the book, namely, treating every new pattern as if it were a new kind of intelligence. It is usually not. More often, it is a new way to route state, control risk, or let the model revisit evidence before it commits. If you keep that lens in mind, the chapter's later sections will feel like extensions of the same architectural logic rather than an assortment of techniques to memorize. Structured reasoning changes how a model behaves, not because it sounds more deliberate, but because it reorganizes the work that happens before the final answer appears. This distinction is central to agent design. A chat completion is a single response. A workflow is a sequence of steps, and an agent is a control loop that revises its next move based on state or tool output. Structured reasoning sits between these forms, reshaping how the model decomposes a problem and how ready it is to act on the result. The shape of the reasoning, the boundaries of the task, the constraints on output, and the existence of an execution surface all matter because they determine whether the model is merely producing plausible prose or actually preparing to act. That distinction is central to agent design. This figure shows how structured reasoning transforms a single response into a control loop. The model makes intermediate commitments, checks them against state or tool output, and revises its next move. That feedback is what makes the behavior more agentic. The practical effect of structure is often underestimated. The model notices one obvious part of the task, rushes to a conclusion, and leaves behind the smaller decisions that would have made the result reliable. When a surrounding prompt forces intermediate organization, the model is less free to collapse everything into one undifferentiated answer. That matters for analysis tasks, planning tasks, and any situation where the final response should emerge from a sequence of check commitments rather than from a single burst of fluent text. Think of it as a notebook versus a monologue. In a monologue, ideas arrive in whatever order sounds natural, and the listener has to reconstruct what the speaker may have meant. In a well-organized notebook, the same work is divided into sections that make the reasoning easier to verify and easier to extend. Structured reasoning nudges the model to separate observation from interpretation and interpretation from action readiness. That separation is especially valuable in agentic systems because they fail more often from hidden shortcuts and premature commitment than from lack of raw fluency. This is why prompt length alone is not the relevant variable. A long prompt that repeats the same demand in different words does little except add noise. A shorter prompt that imposes a clear sequence of analysis can improve reliability because it changes the model's internal ordering of attention. The model is no longer just being asked for an answer. It is being asked to shape the answer through an explicit process. That process can later be paired with tools, search, or routing logic, but the first gain comes from making the intermediate work visible enough to steer. Chain of thought is often described as asking the model to think step by step, but the real value is in staging the reasoning into explicit phases before the final answer appears. That staging turns chain of thought into a control pattern, not just a prompt trick. The point is not theatrical transparency or a wall of text. It is to force the model to decompose the task before resolving it, which reduces the chance it leaps over a necessary step. Chain of thought does not guarantee correctness by itself, but it makes the reasoning process more disciplined. In a data analysis setting, that means describing the dataset first, then identifying patterns or trends, and then summarizing the insight. In planning, it might mean enumerating constraints, comparing options, and then making a recommendation. The model is told the answer should not appear all at once. It should be assembled from explicit stages that are easier to inspect and align with the task. When a model must describe what is present before interpreting what it means, it is less likely to confuse observation with inference. When it must identify trends before drawing conclusions, it is less likely to overfit to a single salient detail. The point of stepwise reasoning is steering, not persuasion. A well-structured chain of thought is closer to a disciplined work memo than a performance of intelligence. A travel assistant with flight options, hotel rates, and policy constraints can be prompted to work through those inputs in order. A data assistant with a table can inspect the shape first, then compare values, then report the conclusion. If the analysis is wrong, the mistake can be localized to the phase where the reasoning drifted. This prompt specifies the structure of the analysis, not just the level of detail. It asks the model to organize the work into a sequence: dataset description, pattern discovery, and insight summary. That three-part flow is a concrete example of chain of thought as staged output, and it makes the reasoning process easier to audit because each stage has a different purpose and a different kind of failure. If the dataset is misdescribed, later steps are built on the wrong foundation. If the patterns are overstated, the summary inherits that error. If the summary is vague, the earlier stages may still reveal whether the model had enough evidence to do better. The staging gives both the model and the reviewer a clear structure to work with. Explicit analysis phases turn chain of thought from a vague instruction into a workflow contract. The model is not merely told to think carefully. It is told what careful thinking means in this task. In a data analysis workflow, this often means three phases: a description phase, a trend discovery phase, and a synthesis phase. The description phase forces the model to inspect the dataset as an object rather than as a source of immediate conclusions. The trend phase pushes it to compare values, look for regularities, and notice anomalies. The synthesis phase asks for judgment only after evidence has been organized. That progression reduces the risk of skipping over the factual basis of the answer. The benefit of explicit phases is that they control attention. A model asked for a direct answer may seize on the most salient part of the input and ignore the details that actually matter. A model asked first to describe the dataset is more likely to verify the schema before interpreting the values. A model asked to identify patterns is more likely to compare across rows or columns instead of fixating on one conspicuous observation. A model asked to conclude only after those earlier stages is less likely to confuse observation with interpretation. This is one of the simplest and most effective ways to make the system more reliable without changing the underlying model. The same structure changes the failure mode. In free-form prose, a mistake can disappear into a fluent paragraph that looks reasonable at a glance. In staged output, the error is tied to a phase. A wrong column reading contaminates the description. An unfounded trend appears in the pattern stage. An overconfident conclusion stands out if the earlier evidence was thin. That visibility is valuable because it makes debugging possible. The surrounding system can compare the stages against the input or against tool output and decide where the reasoning drifted. Structured output is therefore not just a presentation style. It is a mechanism for turning a response into a sequence of commitments. There's also a broader architectural point. A workflow is easier to control when its intermediate state is explicit. An agent is easier to build when a model's reasoning can be separated into named phases that later logic can inspect or reuse. Even before any tool is involved, the structure of the output helps define what counts as a valid analysis. It tells the system where the reasoning should begin, where evidence should be collected, and where judgment should be expressed. That is why structured reasoning is so often the bridge between a plain prompt and a more capable agent loop. Structured reasoning brings real benefits, but it also has clear limits. Let's look at what it actually improves and where it falls short. When a model separates dataset description from trend identification, it is far less likely to skip an essential observation. Reporting intermediate stages makes the path to the conclusion inspectable, and a predictable output shape makes integration with other system parts easier. Chain of thought is an engineering control as much as a reasoning aid. It gives the system an organized place to look for evidence, assumptions, and conclusions. A fluent analysis can still be wrong. The model may misunderstand the data, infer a trend from noise, or produce a polished explanation that never touched a real computation. Well-structured reasoning can sound authoritative even when it is detached from the actual task. So practitioners should treat visible reasoning as a hypothesis about the answer, not as proof that the answer is right. In numerical or data-bound tasks, prose alone should not be trusted to invent the answer. The model can suggest what should be computed, but the computation itself should be checked against execution whenever possible. Structured reasoning shapes the path to the answer. It does not certify the answer. The more consequential the claim, the more important it becomes to pair the reasoning trace with a tool that can ground the conclusion in computation. When the problem is bounded and the risk of error is moderate, a single structured reasoning path is often enough. But when the problem is ambiguous, combinatorial, or highly contingent on which interpretation turns out to be best, forcing one chain may be too restrictive. The model benefits from considering multiple candidate paths rather than one prescribed one. That is where branching search becomes relevant, but only after the distinction between reasoning and proof has been made clear. Reasoning about an answer and computing an answer are fundamentally different activities. Separating them makes the system more reliable because the model no longer has to invent results that should be computed. A sandboxed Python runtime creates a separate execution surface for computation. The model handles decomposition, interpretation, and planning, while the tool handles exact calculation, data loading, and producing runtime output that can be inspected. When those responsibilities are separated, the system becomes more reliable. Consider a data analysis task with a large CSV. The model infers the schema, decides which summaries matter, and chooses a plausible analysis path. But the actual statistics should be produced by execution. The sandbox loads the data, prints summaries, and exposes the values needed for interpretation. That execution layer acts as a truth check below the language layer, where claims are verified by computation rather than by confidence in the wording. This code creates a sandbox Python tool using Pyodide. The description tells the model that the runtime is for data analysis, that results need to be printed, and that pandas is the expected library for tabular work. It also constrains expectations by noting that charts must be emitted as SVG strings and that the sandbox file system is not visible to the host. Those details define what the execution layer can reliably return and shape how the model plans the code it generates. The tool description is part of the agent's usable instruction surface. It tells the model exactly what the sandbox can do and what it cannot. A well-described tool lets the model choose actions that are more likely to succeed the first time, reducing wasted attempts and improving reliability. The separation also improves debugging. If the analysis answer is wrong, there are now distinct failure modes to inspect. The prompt may have been weak, the code may have been wrong, the tool output may have been incomplete, or the model may have misread the result. Without a sandbox, those possibilities blur together. With a sandbox, they're separable, making iteration much more effective because it is clear whether the problem was reasoning, execution, or interpretation. A tool description is a contract, not decoration. It defines what the model can do and how results must be returned. When a sandbox says it executes Python for analysis, that sets the domain of valid use. When it says results must be printed, that defines the output protocol. And when it notes the host cannot see the sandbox file system, it warns the model not to rely on hidden side effects or invisible state. This is the language of an interface boundary, and that boundary matters because the agent is most dependable when the model and the runtime agree on what counts as a valid action and a valid result. That contract is important because it shapes the model's planning. If the tool expects printed output, the model should write code that emits visible results rather than quietly mutating variables and hoping the host infers the outcome. If the tool expects pandas tables, the model should structure its analysis around tabular operations rather than ad hoc text manipulation. If the tool has runtime limits, the model should keep its analysis inside a realistic computational budget. The contract, therefore, does more than expose capabilities. It channels reasoning into a form that the execution surface can actually satisfy. Seen this way, the sandbox is an intentional limit on imagination. The model is not free to invent the answer when the answer should be computed. It has to propose code, run it, observe the return output, and then summarize that output. That pattern is valuable even before any broader orchestration is added because it makes a common failure mode much less likely. The model convincing itself that a calculation has been done when it has not. The reason the sandbox matters is not that it makes the agent mysterious. It matters because it makes the difference between imagined results and executed results concrete. A reasoning prompt and a sandbox tool become much more powerful when they are bound into a single agent object. That binding is the bridge from instruction shaping to operational behavior. The prompt tells the model how to organize its analysis. The tool gives it a place to execute code. The agent wrapper coordinates the two so the model can alternate between planning and execution under one interface. Even in a minimal setup, that is a meaningful architectural shift because the model is no longer just producing text that happens to mention analysis. It is participating in a controlled loop. This small construction call carries a large idea. The model receives the staged analysis prompt. The tool list exposes the Python sandbox. The agent constructor binds them into a system that can choose when to answer directly and when to compute first. The important point is not the syntax. It is the control flow implied by the syntax. The model is being asked to reason in stages, to execute when needed, and to return a final answer that is grounded in the output of the tool when the task requires it. That is the bridge from prompt design to agent implementation. The same structured reasoning that makes a single response easier to inspect can become part of a larger loop in which the model plans, acts, observes, and reports. In a data analysis setting, that means the system can inspect the input, generate code, run the code, read the output, and summarize the result without collapsing those steps into one opaque completion. The agent wrapper does not replace reasoning structure. It operationalizes it. This is also why structured reasoning and tools fit together so naturally. The prompt narrows what kind of analysis the model should perform. The sandbox narrows what kind of proof it can provide. The agent binds those constraints into one controlled sequence. Once that connection is in place, it becomes much easier to understand why some tasks can be solved with a single structured pass, while others benefit from branching exploration. Not every task needs search, but some tasks need more than one path considered before the system commits. Tree of thoughts turns reasoning into a branching search process. Instead of following a single line of analysis, it generates multiple candidate paths, evaluates them, and selects the best one before committing to a final answer. Chain of thought asks for one ordered line of analysis. Tree of thoughts asks for several candidate lines, judges which ones look promising, and prunes the rest before acting. It is a practitioner pattern for handling uncertainty by comparing alternatives rather than trusting the first plausible route. Generation produces candidate thoughts or partial solutions. Evaluation checks those candidates against criteria like correctness, feasibility, or cost. Selection keeps the most promising branches and drops the rest. This matters whenever the task has more than one plausible direction, and choosing the best one matters more than picking the first acceptable one. The diagram shows several branching paths radiating from a starting point. Some paths are marked as weak and pruned early. Others continue to deeper evaluation. The final answer emerges only after comparing and selecting among the surviving branches. Chain of thought is like following a single well-marked hiking path from start to finish. Tree of thoughts is like a network of paths where you inspect one route, compare it with another, and prune the ones that dead end. That extra exploration costs more, but it prevents marching confidently into an avoidable mistake. Chain of thought asks how to keep one analysis path disciplined. Tree of thoughts asks how to choose among several possible paths before committing. A linear chain can fail by omitting an essential step. A branching tree can fail by exploring the wrong candidates. TOT is a different control structure, appropriate when the cost of a wrong early commitment is high. The most useful way to compare chain of thought and tree of thoughts is through control flow. Chain of thought is linear and staged. It assumes the main challenge is keeping the model on one discipline path. When the question is straightforward, the data is clean, and the answer is a bounded summary of observable patterns, a well-structured chain often performs well without extra machinery. Tree of thoughts is branching and evaluative. It assumes the main challenge is inspecting more than one path before deciding. This becomes valuable when uncertainty is about the route itself. For example, when a travel assistant must decide between lower cost, lower travel time, or higher convenience, or when a support workflow fits more than one policy interpretation. A single chain can be too eager to collapse ambiguity, but branching search keeps alternatives in view long enough to judge them against the constraints. The trade-off is cost. Linear decomposition is cheaper in tokens, easier to debug, and simpler to combine with one tool call. Branching search uses more computation, creates more intermediate state, and can become unwieldy as the number of branches grows. That is why TOT should be reserved for tasks where the cost of a wrong branch is greater than the cost of exploring alternatives. On simple extraction or arithmetic, it is often unnecessary overhead. On planning, diagnosis, or multi-constraint decisions, it could be the difference between a brittle guess and a robust result. The practical failure mode of COT is underuse, skipping decomposition that would have prevented a mistake. The practical failure mode of TOT is overuse, making every task a search problem, which gets slower, noisier, and more expensive without proportional improvement. A good rule of thumb: use structured COT when the task needs a single well-ordered analysis path. Use TOT when the task presents multiple plausible routes and the cost of choosing badly is high enough to justify the extra branching. The reasoning pattern you pick for an agent task should be driven by the shape of the work, not by what technique happens to be available. A structured chain of thought works well when subtasks are clear and the main risk is skipping a step. Tree of thoughts is worth the extra cost when there are multiple plausible paths, and premature commitment is the danger. And for tasks that depend on exact computation or factual verification, neither pattern alone is enough. You need a tool that can compute or check the result, which is why a sandbox Python runtime pairs so naturally with structured reasoning. A data analysis example makes this concrete. If the model only needs to summarize a small, obvious table, a stage prompt may be enough. But if the table is large or the relationships are subtle, the model should use the sandbox to compute summaries instead of relying on textual inference. And if the analysis has several competing interpretations, a branching approach helps the model compare candidate explanations before selecting one. The goal is not to maximize sophistication. It is to match the control pattern to the uncertainty of the task and to the acceptable cost of error. A useful practitioner instinct is to think of these patterns as budgeted controls. Chain of thought spends a little structure to reduce omission and improve clarity. Tree of thoughts spends more structure to reduce bad commitment under ambiguity. A sandbox spends execution resources to replace guesswork with computed evidence. The strongest systems combine those selectively. They do not ask the model to do everything in prose, and they do not ask it to search blindly when a clear analysis path exists. They use structure to narrow the problem, search when alternatives matter, and tools when claims need proof. That combination is the real transition from prompt engineering to agent design. Once the model's intermediate work is structured and its claims can be verified, the surrounding system begins to behave less like a chat interface and more like a bounded decision engine. The next sections can then add stricter control flow on top of that base. The essential premise remains the same. Agent behavior is shaped not only by what the model knows, but by how its reasoning is organized before action and how its reasoning is checked after it acts. That combination is the real transition from prompt engineering to agent design. Once the model's intermediate work is structured and its claims can be verified, the surrounding system begins to behave less like a chat interface and more like a bounded decision engine. The next sections can then add stricter control flow on top of that base. The essential premise remains the same. Agent behavior is shaped not only by what the model knows, but by how its reasoning is organized before action and how its reasoning is checked after acts. Tree of Thoughts gave us a way to explore multiple reasoning paths, but it didn't have a mechanism for persistent state or conditional loops. React adds those. It lets the model maintain a running state, loop over steps, and decide when to branch or stop based on what it has observed. Tree of Thoughts and React are often mentioned together because both insert intermediate steps between a prompt and a final answer. But the engineering difference is not cosmetic. Tree of Thoughts explores branches. React runs a closed-loop control cycle. Tree of Thoughts generates several candidate continuations, evaluates them, and keeps the most promising branch. React repeatedly emits a decision, a tool call, or a reasoning step, receives an observation from the environment, and then chooses the next action based on updated state. One improves selection, the other governs interaction. The left side of the figure shows Tree of Thoughts generating multiple reasoning paths and pruning them before execution. The right side shows React's loop. The model takes an action, receives an observation, and feeds that back into the next decision. The key difference is that React's loop actually interacts with the environment. A useful analogy is route planning versus driving. In a T-style workflow, the agent compares several possible routes on a map before anyone starts the car. In a React loop, the car is already moving. The driver checks traffic, listens to directions, calls for assistance, and reroutes as conditions change. Both involve alternatives, but only one acts on the world while reasoning. A larger prompt can make a one-shot model answer more carefully, but it does not create a bounded mechanism for trying a step, observing the result, correcting course, and halting safely. Agentic behavior comes from orchestration over state. The state preserves what has already happened, the loop decides what happens next, and routing determines whether the system continues or stops. The most common mistake is to treat verbose reasoning as if it were equivalent to executable control. A model may write a detailed justification for an action and still fail to issue a valid tool call, or it may issue a perfectly shaped tool call while the reasoning text is misleading. In production systems, what matters is the reliability of the control flow, not the theatrical quality of the explanation. Tree of thoughts is often described as a reasoning method, but when you look at it from a system perspective, it behaves much more like a workflow optimization than an autonomous agent. The key difference is that the graph is staged, the control logic stays external to the model, and the system never acts on the world until after the branching is done. The process is staged. One node proposes candidates, another evaluates them, and a later node consumes the selected branch. That sequencing is deterministic in the orchestration layer, even though the model outputs are probabilistic. The system is not deciding what external action to take in response to an observation. It is deciding which internal path to continue. The branch set is finite, explicit, and pruned before any expensive downstream work begins. That constraint is actually what makes Tot valuable. A small generator can cheaply produce several possibilities, and a stronger evaluator acts as a judge to select the candidate that best satisfies quality, novelty, or feasibility criteria. For example, in a travel assistant, you might generate an economy-first route, a fastest route variant, and a comfort-weighted variant, then select the one most aligned with the user's constraints. The system is not acting on the world in each branch. It is creating a controlled set of options for later execution. This distinction also clarifies why Tot and Cot are related but not interchangeable. Chain of thought is a linear structuring of intermediate reasoning. Tree of thoughts is a branching structuring. Cot asks the model to articulate a single path, while Tot asks it to generate multiple paths and then prune them. Both are about internal deliberation, but neither alone creates a loop that interacts with tools over time. A workflow can use Tot upstream of an agent, but the branching stage itself remains a workflow stage, not an autonomous runtime policy. In practical terms, Tot is best understood as a workflow boundary that improves a later decision. If you need a plan outline, a short list of hypotheses, or a set of ranked approaches before invoking heavier systems, Tot is compact and effective. But if you need the system to search the web, inspect a calendar, validate a quote, ask for approval, and then continue based on the result, Tot alone is not enough. The loop must be able to absorb observations and return a policy selection. That is the point at which the architecture becomes agentic. React becomes clearer when you think of the model's output as operating in an augmented action space, not just a single stream of text. Formally, the effective action set is the union of two sets: A, the task actions like tool calls, and L, the language set for reasoning traces. This equation captures the core idea. The model chooses from a combined space where narrative reasoning and executable actions are both valid outputs. The model isn't just deciding what to say or what to do separately. It picks from a unified space where both reasoning traces and tool calls are control-relevant outputs. That two-language contract is the heart of React. This changes how the runtime interprets a model response. Pure language gets recorded as a thought or summary. A tool call directive gets dispatched to a function, and the observation feeds back into the next state. The model output is a mixed signal, part explanation, part control instruction. The next equation makes the iterative structure explicit. The context at the next step is the previous context with the current augmented action appended. This means the loop is cumulative. The agent doesn't restart from a blank prompt each turn. The context becomes a travel log of the run: what was tried, what was learned, and what remains unresolved. For a travel assistant, that might include target dates, search results, a price quote, and a pending approval request. The policy view is equally important. This reads as the policy selecting the next action from the current context. The model's next move is conditioned on everything the loop has accumulated so far. The policy is not producing a free-floating completion. It is making a decision in a stateful process, where the choice to think, call a tool, ask a question, or stop depends on the current accumulated context. React is a control policy over a changing execution state. The final equation makes the state-machine interpretation even more concrete. Context is an ordered sequence of observations and actions up to the current observation. The runtime remembers what happened in sequence, so the next decision is made with awareness of the path already taken. That ordered history is the operational state of the loop, not long-term memory or a static prompt template. A React agent knows something because the relevant observation is still present in the state, not because the model has permanently learned it. A single prompt has no memory between turns. To iterate, an agent needs state, preserve information that shapes each subsequent decision. In a plain chat completion, the model answers once and the turn ends. In a React loop, each turn leaves behind machine-readable state, message history, tool outputs, pending actions, route metadata, or loop counters that influences the next turn. The model can only behave consistently if that state is carried forward without ambiguity. That is why a message stream is such a natural representation of React state. The model's prior statements, tool requests, and tool observations are not just transcript artifacts. They're the evolving substrate of the next policy decision. When a turn begins, the runtime assembles context from system instructions, the state, and the most recent messages. After a tool call, the observation is appended back into the same stream. So the agent reacts to reality rather than to its own last guess. A prompt template describes how the model should behave. State describes what has actually happened. If you blur those together, systems become brittle in exactly the ways production agents tend to fail. The model may see the latest user request, but if it cannot also see tool results, approval status, or the current branch, it will hallucinate continuity that the runtime does not possess. For Atlas Travel Assistant, state might record a destination preference, a budget ceiling, two alternative fares, and an unresolved approval gate for a non-refundable booking. That is a much richer situation than a simple prompt containing the user's original request. The agent can respond differently because the state has changed. Each observation reshapes the next action space, and the state machine is the mechanism that preserves that accumulation. A React loop needs a reliable way to turn the model's suggestions into actions the system can actually execute. That's what structured output and tool binding provide. Tool binding gives the model a declared set of tools it's allowed to call, each with a schema for valid inputs. Structured output lets the runtime parse the model's intent deterministically instead of guessing from natural language. Together, they turn a free-form textual suggestion into a machine-routable instruction. The pattern starts by defining a state that holds a sequence of messages, and then binding tools to the model so it can emit both narrative and action-oriented outputs. The state is a typed dictionary with a messages field. The add_messages annotation tells the runtime to append new messages to the list rather than overwrite it, which is exactly what we need for a conversation. We create the model and then bind it to a set of tools. The bind_tools call constrains the model so its output can include structured tool call requests that the runtime can dispatch safely. Without binding, the model can still talk about tools, but the runtime can't safely treat its words as executable action. With binding, the tool call portion becomes a structured event that can be dispatched or rejected. That's the difference between saying, "I should look up flight options," and emitting a valid request that actually invokes the flight search tool. The agent step itself is straightforward. It consumes the current context and returns the next message, which could be reasoning text or a tool call request. This function is the policy node. It invokes the model with the system prompt and the current message history, then returns the response as a new message. Notice it does not execute tools directly. It only decides what the next move should be. The graph runtime interprets the model's output according to routing logic. This separation of concerns keeps the model's role narrow and inspectable. It proposes the next action, but the runtime remains responsible for deciding whether that proposal is executable, safe, and complete. A malformed tool call is a classic failure mode. The intent may be correct, but if the tool name is unknown, the arguments don't match the schema, or the output lacks routing metadata, the action cannot be executed. Structured output and tool binding are what make the label machine readable. Once tool binding is in place, the React loop becomes a concrete state machine. The runtime executes the policy node, inspects the output, dispatches tools if needed, appends observations, and returns control to the policy node. This sequence, think, act, observe, route, repeat, transforms the agent from a monolithic generation into a bounded loop over explicit transitions. The logic is simple enough to describe in one breath, but the architectural consequence is substantial. The agent becomes a bounded loop over explicit transitions instead of a single monolithic generation. The tool node is where the loop touches the outside world. It is deliberately deterministic. It does not decide strategy, it executes requests. This function reads the last model message, extracts any tool calls, looks up the corresponding function, and emits tool messages that represent the observations returned by the environment. That observation then becomes part of the state the policy sees on the next iteration. In a travel assistant, this might be a price quote, a set of available dates, or a booking confirmation candidate. The system does not merely hope the model remembers what it asked for. It records the result as state. The policy node sees the current context and decides to call a flight search tool. The tool node executes that search and returns results. Those results are appended to state. On the next policy pass, the model sees not only the original request, but also the search result. It can then choose to search again, compare options, ask the user for clarification, or stop. A pipeline moves forward once. A loop returns to the decision point after every observation. That return path is why React is operationally different from Tree of Thoughts. Top prunes branches before execution proceeds downstream. React revisits the decision point after the environment responds. The branch can change because the world changed. A loop needs a way to decide when to stop. In a React system, that decision is made by a routing predicate that checks the latest model output and chooses whether to continue to a tool or end the run. The predicate is not an optimization hint. It is a control boundary. It looks at the last message from the model and decides the next step. This function checks the last message. If it contains tool calls, the function returns continue and the graph proceeds to the tool node. Otherwise, it returns end and the graph halts. This is not about trusting the model to know when it is done. The runtime enforces a policy that prevents open-ended loops where the model keeps producing tool-like language without a valid action, and also prevents premature termination when the agent still needs information. The agent node approaches the intersection with a candidate action, but the predicate decides whether to proceed onto the tool road or stop. Without that traffic light, every turn would be ambiguous, either overrunning the loop or stopping too early. When the graph routes from policy to tool, that is a handoff from decision-making to execution. When it routes back, that is a handoff from execution to reflection. The handoff is the mechanism that keeps the loop coherent across nodes and phases. In production, the predicate often needs additional safeguards beyond simple tool call detection. You might bound the number of iterations, require certain tools to be called at most once, or stop if a requested tool is no longer available. These are guards around the loop, not elaborations of the model. The React loop becomes visible when you wire it as a graph. Nodes represent the agent and the tools, edges control the flow, and a return path from tools back to agent keeps the cycle going. Each piece of the React pattern maps to a graph element. The agent node is the policy that decides what to do next. The tools node carries out the chosen action. A conditional edge checks whether to continue or stop, and a fixed edge from tools back to agent closes the loop, turning a single step into an ongoing cycle. Here is the actual graph construction. We create a state graph with our agent state, then add two nodes, agent and tools. The entry point is set to agent. The conditional edge from agent uses the should_continue function to decide whether to route to tools or to Yendi. Finally, a fixed edge from tools back to agent completes the loop. Compiling the workflow produces the runnable graph. The node names are not arbitrary. The agent node selects the next action from the current state. The tools node executes that action and records the observation. The conditional edge is the continuation policy that decides whether to keep going. The fixed edge from tools back to agent is the return path that turns one iteration into a loop. This is the graph equivalent of think, act, observe, repeat. Because the control flow is explicit debugging becomes much easier than in an opaque prompt chain. You can inspect the trace and see exactly which node ran, which tool call was omitted, which observation came back, and which route was chosen next. That visibility matters when a loop behaves oddly. A premature stop may reveal that the policy output omitted a tool call. An infinite loop may reveal that the same observation keeps triggering the same action because state was not updated correctly. A malformed tool call may reveal a schema mismatch rather than a reasoning failure. The graph also makes checkpointing and resumption natural. Once execution is represented as a state machine, the runtime can pause between nodes, resume after an interrupt, or hand off control without losing the current state. React is therefore not just a clever prompting pattern. It is a reusable execution structure that can be paused, inspected, and continued because the loop is encoded in graph semantics instead of hidden in ad hoc application code. Tree of thought and React are often discussed as separate strategies, but in a real system, they can work together. This part shows how to combine them cleanly, keeping each pattern where it is strongest. Think of Tree of Thought as an upstream optimization stage. It explores multiple candidate plans, scores them, and selects a promising one. For the Atlas Travel Assistant, that might mean choosing a route that balances price and travel time. Once a candidate is chosen, React takes over as the downstream execution policy. It interrogates tools, validates availability, gathers observations, and adjusts the plan as new information arrives. The first phase reduces search cost and improves initial quality. The second phase ensures the plan survives contact with reality. This division of labor preserves the right abstraction boundary. Tree of Thought is about exploring candidate reasoning paths inside a control workflow. React is about operating an iterative policy over a live state. If you collapse them, you lose clarity about where search ends and execution begins. If you keep them separate, you can use each pattern where it's strongest. A planner can produce a promising route. A React loop can drive the car. In practice, the same system may contain both a branch scoring stage and a tool using loop, but they solve different problems. The former chooses among possible plans. The latter carries out one plan, while adapting to fresh observations. That separation is what makes the architecture legible, testable, and safer to extend. An agent loop that looks elegant on paper can fail in practice. Understanding the common failure modes and knowing when not to use a loop at all are essential design skills. The most obvious failure is an infinite loop. If the policy keeps producing tool calls and the routing predicate always returns continue, the graph spins forever unless you enforce explicit stopping conditions. This can happen when a model fails to converge, when observations never change in a way that resolves the task, or when the graph simply lacks a termination guard. A React loop without a halting policy is not an agent. It is an unbounded process. A second failure mode is premature termination. The model may output a natural language completion before it has actually resolved the task, or the router may misinterpret a malformed message and stop too soon. The system appears fast and confident, but it is only incomplete. This is why the distinction between reflective text and executable control signals is so important. The runtime must know which parts of the output are commentary and which parts are action. A third failure mode is invalid tool invocation. The model may request a tool that is not registered, pass arguments that do not match the schema, or generate a call that cannot be routed because the output structure is broken. Structured output and tool binding reduce this risk, but they do not eliminate it. The runtime still needs to validate names, shapes, and result handling before trusting the call. That validation is the practical counterpart to the theoretical idea of an augmented action space. The deeper design boundary is knowing when not to use a loop at all. If the task is a single deterministic transformation, a simple workflow, or even a one-shot prompt may be enough. React adds value when the task benefits from environment interaction, iterative correction, and bounded autonomy. Tot adds value when you need candidate exploration before execution. The architectural discipline is to choose the smallest control structure that can still represent the task safely. That is the skill this section is meant to establish. Not just understanding the names of the patterns, but recognizing which kind of control flow a problem actually demands. This figure shows how React context accumulates. Each step appends the current augmented action, the thought, tool call, and observation, to the prior state, producing the next decision context. Notice how the state grows with each iteration, giving the model a complete history to reason from. Human in the loop is not a decorative safety slogan. In a production agentic system, it is a controlled decision embedded directly into execution semantics. The moment you decide that a human must inspect, alter, authorize, or supply information before the system advances, you're designing a workflow with explicit governance points. This distinction matters because the same model output can have very different operational meaning depending on whether it is allowed to proceed automatically, paused for review, or converted into a human visible checkpoint. The control layer determines who has authority over state changes, who can authorize side effects, and which transitions remain reversible. Consider the Atlas Travel Assistant. A purely conversational assistant can describe flight options, but it cannot safely commit to a purchase on behalf of a user just because it is confident. A bounded autonomous travel agent can research itineraries, compare trade-offs, draft a booking request, and then stop at an approval gate before executing the irreversible action. The architecture decides whether reasoning ends in a message, a state update, a tool call, or a pause. A useful analogy is a train line with signal stops. A plain chat response is like a station announcement, informative but not operationally constraining. A workflow is a track with predefined switches and stop points. An agent adds a decision-making engine that can choose among permissible routes at each stop. Human-in-the-loop inserts a staff signal box into that route, where the line can be held, inspected, redirected, or released. The figure shows the execution graph with a human-in-the-loop checkpoint inserted as a first-class node. The agent's path passes through this gate, where a human can inspect, approve, or modify the state before the workflow continues. This is not an external afterthought. It is an explicit part of the execution flow. This is why bounded autonomy is the right framing. The goal is not to eliminate autonomy. That would just be a scripted workflow. The goal is to constrain autonomy so the agent can act within a designed envelope while still deferring high-risk, ambiguous, or externally visible steps. Some turns are fully automatic, some are interrupted for oversight, and some are only annotated for later inspection. A mature agent architecture treats these distinctions as first-class parts of the loop. When human review happens outside the workflow, the system becomes hard to reason about. Embedding it into the graph keeps the execution model coherent. The pause, the review, the response, and the continuation are all part of the same state machine. If human review happens outside the workflow, the system becomes difficult to reason about because the run state, the human decision, and the eventual continuation are all managed by separate and formal processes. That may work in a prototype where an operator watches a screen and manually clicks a button, but it quickly breaks down when multiple runs are active, when retries occur, or when the system needs an audit trail showing exactly which version of state was reviewed. This matters for auditability as much as for safety. When a workflow pauses inside the graph, the current state is persisted in a way that can be inspected later. The decision is attached to a particular execution point, not just to a vague moment in a support dashboard or ticket thread. That gives you a durable account of what was known at the time of review, what was approved, what was edited, and what branch the run took afterward. Pulse Support Orchestrator makes the contrast even clearer. In customer support, many human touchpoints are not about authorizing a dangerous external action. They're about escalation, policy interpretation, or correction of an incomplete classification. A support agent may route a ticket to a specialist, ask a human to clarify a policy edge case, or let a reviewer edit a response before it is sent. The architecture needs to know whether a human is reviewing a recommendation, modifying the working state, validating a user-provided detail, or granting permission for an external side effect. There is also a practical reliability reason to model the interaction in the graph. Agent runs fail in many ways that are not simple model errors. The data may be stale, a tool may return a partial result, a policy may require a second pair of eyes, or the system may need missing information before any further progress is meaningful. A graph-based HITL design allows the execution engine to pause exactly where the uncertainty arises. It does not need to continue guessing, and it does not need to throw the entire run away. The word interrupt gets thrown around loosely, so we need a precise, operational taxonomy. An interrupt is a deliberate pause in workflow execution at a specific point where a human may intervene under a defined permission model. The key is not just that a human is involved, but what kind of intervention is requested, what object it applies to, and what becomes legal afterward. The critical question is not simply whether a human is involved, but what sort of intervention is being requested, what object the intervention applies to, and what downstream transition becomes legal afterward. The same pause mechanism can support very different control intents, and collapsing them into a single human review bucket hides those differences. The first family is approve or reject. Here the workflow has already formed a proposed action, usually one with side effects, and now requires a human to authorize it. The human does not merely comment. They decide whether the action may proceed. This is the classic approval gate. In Atlas Travel Assistant, this is the moment before a booking request is submitted to an airline or hotel API. The agent may have a well-formed itinerary, but the architecture still requires explicit permission before money is spent or an external reservation is created. The allowed human response is structurally narrow because the action itself is structurally sensitive. The second family is review and edit state. In this case, the human is not only observing the machine state, but may modify it before the workflow continues. That is a different authority model. The human is not authorizing an external effect. They are correcting the agent's working representation, perhaps because a destination, date, budget constraint, or policy flag is wrong. The effect is internal to the run, not external to the world. This kind of interrupt is especially useful when the agent state is incomplete or stale, because the model can resume from a corrected snapshot instead of carrying forward an error that would otherwise contaminate later steps. The third family is review tool calls. This is narrower still. The human inspects the intent or arguments of a tool invocation before the tool is actually invoked. The workflow may have decided that a lookup, request, or mutation should happen, but the human gets to see the exact parameters before the system touches the database, API, or other external resource. That matters because a tool call can be perfectly reasonable and abstract, but still dangerous in its concrete form. A draft email, for example, may be acceptable as a concept while the recipient list or attachment content is not. Reviewing the tool call gives oversight at the most local possible point before the side effect. The fourth family is validate human input. Here the human is not approving a machine action at all. They're supplying or correcting information that the workflow needs in order to continue. This is often confused with approval because both involve a pause and a person, but the trust model is different. In validation, the human is effectively part of the data path. The workflow is waiting for missing facts, confirmations, or corrections, not for authorization to act. In a travel workflow, that might mean asking the user to confirm whether they prefer non-stop flights or lower total price before search continues. In a support workflow, it may mean asking a human reviewer to supply a missing policy interpretation that classifies the issue correctly. A compact way to distinguish these families is to ask 3 questions. Who is the actor at the interrupt point? What may they mutate? And what does their response unlock? Approval changes permission for an external action. Review and edit changes the run's working state. Review tool calls changes the exact parameters of a pending side effect. Validation changes the information on which the system will reason next. Once those roles are separated, the downstream workflow can enforce the correct semantics without ambiguity. This diagram lays out the 4 families side by side. Notice the columns for actor authority, what can be mutated, and what the response unlocks. Approval gives authority over external side effects. State editing lets the human change internal working memory. Tool call review focuses on the exact parameters of a pending call. Validation fills in missing data. The matrix makes the differences clear at a glance. The practical difference becomes even clearer if you compare them along the dimensions of authority, permitted mutation, and downstream consequence. In approve or reject, the human has authority over whether a pending commitment may leave the workflow boundary, but the human usually does not alter the action substance unless the workflow explicitly supports redirecting it. In review and edit state, the human may change the internal representation that future nodes will read, but they're not directly granting permission for an external call. In tool call review, the human evaluates a specific outgoing operation and may block or allow that one operation without rewriting the broader state. In validation, the human is not deciding on machine authority at all. They're contributing missing information, and the system consumes that information as input to the next computation. It is useful to keep a small mental comparison matrix in view when designing these controls. Approval is about who may authorize side effects. Review and edit is about who may correct the workflow's memory. Tool call review is about who may inspect the immediate boundary between internal reasoning and external action. Validation is about who may fill in missing facts so the workflow can continue. That matrix helps prevent the common mistake of treating every human touchpoint as if it were a sign-off step, when in fact many touchpoints are only about correcting a field, clarifying a request, or confirming an assumption. Some actions are commitments, not just high-confidence decisions. Approval gates separate recommendation from execution, protecting the organization from irreversible or costly actions. Confidence alone does not grant authority to commit. A model can be highly confident about booking a flight or issuing a refund, but those actions change the outside world and expose the organization to cost or liability. The gate separates recommendation from execution. A system can be internally uncertain and still draft a harmless summary. Conversely, it can be confident and still need approval before charging a card. The gate recognizes that some transitions require a different decision maker than the one generating the proposal. Even if the UI looks binary, the human response at an approval gate often has three meaningful forms. Approve authorizes the action. Reject prevents it entirely. Redirect returns the workflow to an earlier state with revised constraints, like a traveler rejecting a hotel choice but asking the agent to continue searching under a tighter price cap. Redirect is not a terminal error. It is a state transition. Placing the gate before irreversible or externally visible actions creates a controlled seam in the graph. The system can persist the draft, display the pending side effect, and await a human decision without losing context. This is safer than letting the model fire a tool call first and ask for forgiveness later, and it creates a clearer operational boundary for logging and audit. Review and edit interrupts let a human repair the workflow's internal state before the next step depends on it. This is one of the most powerful human-in-the-loop patterns because it operates directly on the machine-readable substrate that drives routing, tool selection, and termination. If a critical field in the graph state is wrong, every subsequent step faithfully executes the wrong plan. Editing state is not cosmetic. It is surgery on the control substrate that determines what happens next. The distinction from approval is essential. Approval authorizes an external action, but state editing changes the run's internal working memory. For example, if the travel assistant misidentifies an arrival city because the user mentioned a layover, a reviewer can correct the destination and state so the search branches rebuild on the correct assumption. This is like correcting a map before the vehicle proceeds. This category is especially useful when the agent has accumulated stale context. Large language models can be very persuasive even when a small part of the state has drifted. A human edit can restore a loss constraint without restarting the entire run, making the mechanism valuable for both safety and operator efficiency. The downstream implication is that the workflow must treat edited state as authoritative for subsequent routing. If a human changes the budget cap, the next search step must read the updated value, not a cache copy. If the graph does not propagate edited state consistently, the human intervention becomes illusory. The UI shows the correction, but the execution path uses stale values. This is one of the easiest ways for HITL systems to fail in practice. Tool call review is a focus checkpoint. Before the system touches an external system, a human inspects the exact action it is about to take. Instead of reviewing the entire agent trajectory, the human sees the structured tool invocation, like a booking API call or a database write, and can check whether the inputs are correct before the tool runs. This keeps the oversight local and surgical. A reviewer does not need to parse the whole trace to catch an obvious mistake like a wrong date or recipient. They can focus on the actual call surface. For the Atlas Travel Assistant, that means inspecting a reservation payload before submission. For a support orchestrator, it means checking a proposed reply references the correct policy version. Tool call review does not let the human rewrite broader run conditions. It only gates the immediate side effect. That is a feature, not a limitation. Many workflows need a checkpoint precisely because the surrounding reasoning was acceptable, but the action itself deserves a final gate before touching the external system. When the model emits a structured tool call, the approval surface can display exactly what will happen, and the workflow can determine whether the call is safe to execute. Freeform text is a poor substrate because the reviewer must infer structure from language, which is error-prone and slow. Structured tool binding makes the human's role crisp and enforceable. Validation interrupts handle a different kind of human involvement, not approval, not debugging, but providing missing information the workflow needs to continue. In a validation interrupt, the human is supplying a missing fact, confirming a detail, or resolving ambiguity. Execution cannot continue until that input arrives, but the human is not authorizing anything. They're providing data the workflow cannot safely infer on its own. A travel workflow asking whether to prioritize cost or convenience is not asking for permission to buy. It is asking for a constraint that shapes future search. A support workflow asking if a customer is an enterprise account is not asking for sign-off on a side effect. It is asking for classification that controls routing. If you treat these as approval gates, the workflow becomes slower and more cumbersome than it needs to be. The graph pauses just long enough to get the missing fact, then resumes from the correct state. The human does not need to step into a broader review role. This keeps the oversight burden proportionate and separates policy concerns from informational ones. The person who knows the missing detail may not be the same person who should approve a financial commitment. A strong workflow design treats validation as a separate contract. The system should know what kind of data it expects, how to merge the response into state, and whether the response is informative or constraining. A preference may update routing, a correction may override a stale field, and a confirmation may simply unlock the next model turn. These are different downstream effects, and the workflow should distinguish them explicitly rather than encoding everything as generic human feedback. Pause, checkpoint, and resume are three distinct operations that often get conflated, but each plays a specific role in a human-in-the-loop workflow. Understanding the difference is essential for building reliable agents. A pause is the act of stopping execution at a design point. A checkpoint is the persisted snapshot that preserves enough state to continue later. Resume is the act of restarting the graph from that save point after the human response arrives. These are related, but not identical. Without the checkpoint, a pause would be transient and fragile. Without a resume target, the save state would be inert. Without a clear interrupt boundary, neither would be attached to a meaningful control point in the workflow. What is actually paused is not merely the model's thought process. The graph stops advancing, pending side effects are withheld, and the current state transition is not committed beyond the checkpoint. That means a run can be suspended before the system sends a message, books a reservation, writes to a database, or continues to the next branch. In a production agent, that distinction prevents partial actions from leaking through while the human is still deciding. The checkpoint is therefore a protection against both accidental commitment and state loss. Resume has to target the correct pending interrupt, which sounds obvious until multiple runs, multiple branches, or multiple pending reviews are active at once. In simple cases, the human response can be attached to a single pause node. In more complex cases, the workflow may have several outstanding interruptions that need to be matched back to their exact branch and state version. If the mapping is wrong, the human's approval could resume the wrong action or the wrong branch, which is worse than not resuming at all. This is why a resume map becomes necessary as soon as parallel interrupts appear in the design. The cleanest mental model is that a checkpoint is a serialized promise. The workflow has not forgotten where it was, and the next legal transition is still known. When the human intervenes, they are not editing history. They are authorizing a continuation from a known point, potentially with corrected state. That is very different from replaying the whole run from the beginning. A good HITL system minimizes restart work by preserving enough of the local execution context that the agent can continue with stable semantics. A useful operational heuristic follows from that distinction. If a human action changes what the workflow is allowed to do next, the run should pause and checkpoint. If the human action only adds commentary for later inspection, the run may continue while recording the note in state or trace. This keeps the execution model precise. It also avoids the common trap of pausing for every observation, which turns oversight into latency rather than control. Not every human touchpoint needs to stop the graph. The central question is whether the human must change the execution trajectory or simply leave a record. A common mistake is to make every review a hard interrupt, which slows the workflow and burdens operators without meaningful safety gain. The better question is whether the human needs to change the execution path or just leave a note. If it's only annotation, the workflow can continue while preserving the comment in trace or state for later inspection. A practical heuristic: block execution when the human input changes authority, legality, or external effect. Annotate state when the input only improves visibility. For example, deciding whether a booking may proceed requires a hard interrupt. Noting that a response tone seems too terse but facts are correct may only need an annotation unless policy demand a rewrite. The choice depends on whether the note must alter the next transition or simply inform future oversight. Policy review and user experience review should be kept separate. Policy reviewers focus on permission, compliance, and side effects. UX reviewers focus on clarity, tone, and customer experience. Even if the same person performs both roles, the workflow should not assume they are interchangeable. Blocking on every stylistic suggestion is expensive, but ignoring policy concerns because they were treated as mere comments is dangerous. Encode which input is binding and which is advisory. A second heuristic: ask whether the workflow can safely proceed with the human note recorded but unchanged execution. If yes, annotation is enough. If no, the note becomes an interrupt. This is especially useful in support orchestration, where a reviewer might add a comment about account sensitivity or regional policy. Some notes should just follow the trace. Others should trigger an escalation or halt. The graph must distinguish between the two, or the system will either overblock or underblock. Two running examples will ground the discussion of human-in-the-loop patterns. The first is a travel assistant that needs approval before booking, and the second is a support orchestrator that routes cases to specialists for review. Atlas Travel Assistant is a clean example because the domain naturally contains irreversible actions. Search and comparison can run autonomously, but booking a flight or hotel changes the world and involves money, policy, or user commitment. The workflow gathers options, computes trade-offs, and presents a structured booking request. If the human approves, the action proceeds. If they reject, the system revises the plan or returns to search. If they edit the state, the next round of search restarts from the corrected constraints. The same travel example can illustrate a state correction interrupt rather than an approval gate. Suppose the assistant inferred the user is traveling from San Francisco when the actual departure city is San Jose, or it has the wrong return date because of a time zone issue. The human intervention here is not about authorizing a purchase. It is about repairing the working state before any purchase is attempted. The same domain supports multiple interrupt types, which reminds us that the choice of control pattern is driven by the nature of the decision, not by the domain label. Pulse Support Orchestrator demonstrates a different mix of human touchpoints. Support systems often need review-heavy escalation flows rather than approval-heavy purchase flows. A specialist may inspect a drafted response, adjust policy language, validate a classification, or confirm whether a customer's request belongs to a regulated category. The human might not be authorizing a side effect at all. They may simply be correcting the routing or providing a missing interpretation. The workflow still benefits from interrupts and checkpoints, but the goal is precision and escalation discipline. The contrast between these two examples reveals a general rule. The more irreversible, customer visible, or financially material the next step, the more likely the human touchpoint should be a hard approval gate. The more the system is merely choosing among interpretations, refining a draft, or repairing state, the more likely the touchpoint should be review, edit, or validation. Both are human in the loop, but they are not the same thing. The demo menu in this code base is not an algorithm, it is a catalog. It maps out the different human-in-the-loop oversight patterns and makes the taxonomy visible before you get lost in implementation details. By grouping the demos under one chooser, the repository signals that it is organizing several related control modes into one family, not teaching a single monolithic interrupt pattern. Each menu entry corresponds to a distinct operational question. The feedback loop is about iterated human correction. The approval gate is about authorization before side effect. Review and edit is about state surgery. Parallel interrupts point toward resumption discipline when more than one branch is paused. Tool call review narrows the human's attention to the external action itself. Static interrupts for debugging show that pauses can also be used for inspection and instrumentation, not only for governance. Each entry connects an abstract category to a concrete workflow shape. That helps developers avoid category errors, like asking for an approval example when they really need a review and edit pattern, or asking for human feedback when they actually need a hard gate. Making those distinctions visible early is exactly the kind of clarity that production agent systems need. Transition to concrete line graph interrupt behavior. The taxonomy in this section is intentionally implementation agnostic, but it is already pointing toward the mechanics that matter in a graph-based framework. Once a workflow can pause, checkpoint, resume, and route differently depending on the type of human response, the control flow has crossed from ordinary prompting into an executable state machine with governance semantics. The next step is to make that pause and resume behavior concrete, including how pending interrupts are represented, how responses are matched back to the correct branch, and how the graph decides what to do after a human has acted. That implementation detail matters because the taxonomy is only useful if the runtime can preserve it faithfully. Approval, review, edit, and validation are not just labels on a diagram. They are different state transitions with different permissions and different effects on downstream execution. The conceptual foundation is now in place. The next section shows how to encode it without losing those distinctions. Why approval must be modeled as graph control, not post-processing. Approval becomes reliable only when it is part of the execution graph, not an external afterthought attached to the model's last string. If the model emits a request and some separate UI layer later decides whether to let it through, the system has already lost the most important property of a governed agent, a precise, resumable distinction between a proposed action and a committed action. The proposal may have been displayed to a human, logged to a dashboard, or filtered by a wrapper, but the graph itself still has no durable knowledge that a request is pending. That is a subtle but consequential weakness. Once approval lives outside the graph, the runtime cannot deterministically resume from the exact point where the decision was made, cannot encode different outcomes as distinct control paths, and cannot guarantee that a later node sees the same state that the human reviewed. A useful mental model is a database transaction. A proposal is like an uncommitted transaction that has assembled a set of intended rights, but the system has not yet crossed the commit boundary. An interrupt is the pre-commit review point. Approval is the commit. Revision is a controlled edit to the transaction before commit. And execution is the moment the outside world finally changes. That analogy is valuable because it separates intention from effect. In a well-designed graph, the human does not merely inspect a string after the fact. They decide whether the pending action becomes part of the execution path. The graph, therefore, tracks the action as state, and the state in turn determines the next node. This is the architectural shift that turns a conversational system into a governed agentic system. This distinction also clarifies the boundary between a workflow and an agent. A workflow can absolutely include review steps, but if the approval logic is fixed and the model is only filling in blanks, the system is still operating as a control process. An agent emerges when the model participates in deciding what to do next, while the graph constrains which decisions are allowed and when the system must stop. Approval logic belongs inside that graph because it is not merely validation, it is a transition rule. In other words, the model proposes, the graph records, the human decides, and the graph routes. That sequence is what makes the system bounded rather than merely chatty. The most common implementation mistake is to treat prompt quality as the primary safety lever. A stronger prompt may produce cleaner JSON, a more cautious tone, or a better explanation of intent, but none of that substitutes for explicit control flow. If the external side effect is still reachable without a first-class approval branch, then the system is relying on convention instead of enforcement. Convention can be violated by malformed output, retries, partial failures, or future code changes. A graph-level approval gate, by contrast, makes the policy executable. It ensures that the pending action remains pending until a specific branch in stateful control flow authorizes it. Turning an LLM suggestion into a structured proposal object. The first operational move is to convert a free-form model suggestion into a canonical proposal object. This is the moment where the agent stops being a sentence generator and starts behaving like a system that can be reviewed, routed, and resumed. In the Atlas Travel Assistant, the model might be asked to prepare a request for a travel API, but the graph does not want prose. It wants a machine-readable object with fields that identify the target action and its parameters. That object can then be shown to a human, amended, stored in state, and later executed without ambiguity about what the model meant. The structure matters because review happens against an object, not a mood. If the request is represented as a paragraph of text, a human reviewer must infer which parts are instructions, which parts are defaults, and which parts are incidental explanation. If it is represented as a request with explicit fields, the reviewer can see the exact URL, the query parameters, and any default values that were inferred when the model output was incomplete. This separation of intent from presentation is one of the practical reasons structured output is so central to production agent design. It makes the proposal legible to both machines and humans, and it reduces the chance that a revision accidentally alters something unrelated. The request generation node can therefore be understood as a drafting stage. It asks the model to emit only the structured data needed for the next step, then attempts to parse that output into a canonical object. If parsing succeeds, the graph stores the object and state as the proposed request. If parsing fails, the graph falls back to a safe default request rather than stalling in an undefined state. That fallback is not a cosmetic detail. It is the difference between a draft that is imperfect but reviewable and a broken control path that has no stable object to present to the human. A reviewable object is always better than an ambiguous string because the latter leaves too much room for accidental interpretation. The following node illustrates the pattern. Its purpose is not to showcase a sophisticated parser. It is to show that the workflow has an explicit drafting stage, a deterministic state update, and a bounded request object that downstream nodes can trust. Read the structure first, then trace how each line carries the idea forward. What makes this pattern valuable is not simply that it stores JSON. It stores a proposal that has been normalized into a shape the graph understands. The fallback default serves as a guardrail against partial or malformed emission, but it also gives the human reviewer something concrete to correct. That is an important production principle. The graph should never force a binary choice between accepting nonsense and failing closed with no further path. Instead, it should preserve the best available draft, make the assumptions visible, and let the approval branch decide whether those assumptions are acceptable. This is why a proposal object is so much more than an implementation convenience. It is the artifact that allows the system to distinguish a drafted action from an approved action. Once the proposal is in state, the graph can expose it to review, allow revision, and only then move to execution. Without that object, there is nothing stable to revise. There is only a string, and strings are poor control surfaces for governed side effects. Command as the bridge between data updates and next step routing. The command abstraction is the point where a lang graph turns approval into a first-class control primitive. A node can return a command that both mutates shared state and chooses the next node in a single step, which is exactly what approval workflows require. That combination is more powerful than it first appears. In ordinary graph code, state updates and routing are often treated as separate concerns. A function returns data, and static edges decide where execution goes next. That works for simple pipelines, but it becomes awkward when the next node depends on a human decision, a revision to the pending request, or a retry after an edit. In those cases, routing is not static. It is part of the decision itself. The approval gate node is therefore not just a validator. It is a stateful router. It receives the current proposed request, presents it to the human, receives a structured response, and then decides whether to proceed to execution or loop back to the proposal step with an updated request. Because the same return value can carry both the state delta and the next destination, the graph stays coherent. There is no hidden callback chain, no separate event handler that mutates state out of band, and no ambiguity about which branch should run after revision. Figure 2.9. Approval must live inside the execution graph. A proposal is stored in state, reviewed through an interrupt, and either committed to execution or revised and routed back through the same control loop. That unification is especially useful when a human response changes more than one thing. An approval can set the decision to approved, but a revision may replace the URL, merge parameter edits, and mark the request as revised before returning to the gate. Those changes are not incidental bookkeeping. They are part of the control logic because the next node depends on exactly what was changed. Command makes that explicit. The graph is not merely observing a decision after the fact. It is receiving the decision as a state transition. The gate function below shows the pattern in its compact form. The interrupt carries the proposal and a response schema. The response determines the route. The command object carries both the update and the destination. Read the structure first, then trace how each line carries the idea forward. The architectural value here is easy to miss if one looks only at the syntax. Command is not just a cleaner return type. It encodes the transition relation of the graph. A node can say, in effect, given this state and this human response, the next step is that node, and here is the updated state to carry with it. That is exactly what a review loop needs, because approval is not just a filter on output quality. It is a branch in execution. Once this is expressed in graph control, resumption becomes deterministic, because the graph knows what happened before the pause and what should happen after the decision. The practical consequence is that one can build a graph where the model proposes, the human reviews, and the system either executes or revises without ever leaving the execution model of the graph. That matters for reliability, auditing, and testability. It is much easier to reason about a system whose approval path is encoded as a graph transition than one whose approval path is simulated by an ad hoc wrapper around text generation. Designing the interrupt payload as a review contract. An interrupt is the moment where control flow pauses and the human becomes part of the execution path. The most important design question at that moment is not how the UI looks. It is what the human is being asked to act on. The answer should be a structured payload that includes the pending proposal explicitly and constrains the possible responses through a schema. That schema is the contract between graph state and human resume input. It defines what kind of decision the graph is prepared to accept, and it protects the resume step from arbitrary free-form text that would be difficult to interpret deterministically. A structured interrupt payload solves two problems at once. First, it gives the reviewer the exact object under consideration, which reduces ambiguity. Second, it gives the graph a reliable shape for resumption, which reduces parsing risk. A human can approve the proposal, request a revision with a structured update, or provide a substitute response that the graph knows how to route. Because the schema limits the response space, the graph does not need to infer intent from a sentence like, looks fine, except maybe change the limit. It can instead receive an explicit revision object with a field-level update. That makes the resume path predictable and easier to test. It is useful to distinguish interrupt as a control flow event from a UI notification. A comment in a dashboard or a log entry saying awaiting approval does not pause the graph. It merely documents that the graph may eventually need approval. An interrupt actually stops the execution until a resume input is provided. That distinction is fundamental. If the graph has not paused, the side effect may still proceed. If it has paused, the proposal remains pending in state, and no downstream node can run until a human response is attached. In other words, the interrupt is what prevents the system from silently converting a draft into an action. The schema in the interrupt payload also helps with repeatability in production. A reviewable request should always carry the same fields the human needs to decide. If the schema changes too often or admits overly loose input, approvals become inconsistent and resumption becomes brittle. Tight coupling between the pending request and the response schema keeps the operational contract visible. The human reviews exactly what the graph will later use to route, and the graph uses exactly what the human provided to determine the next day transition. Approval, revision, and substitution are three different outcomes. The interrupt step is easy to describe incorrectly because all human responses can look similar at a glance. In practice, there are three different outcomes, and they have different semantics. Approval means the human accepts the pending request as is and authorizes the graph to proceed to execution. Revision means the human changes the request before it is executed, so the graph must merge the edits in a state and loop back to the gate. Substitution means the human response itself becomes the effective action or output, replacing what the model would otherwise have done. These are not variations on the same event. They are distinct control paths with distinct state effects. Approval is the simplest case, but it is not merely a yes/no flag. It is the point at which a draft becomes a committed action. The graph records that the proposal has been approved and routes to the side-affecting node. Revision is more nuanced because it preserves the same pending operation while altering its parameters. The human is not rejecting the task. They are editing the draft of the task. That distinction is particularly important in operational settings, where the action itself may be valid but the exact target, scope, or argument values need adjustment. Substitution goes even further, allowing the human to override the model with a direct response or alternative tool result, which is useful when the model's proposed action is not the right control artifact at all. The reason these outcomes must remain separate is that they imply different safety and observability semantics. Approval means the original proposal is sufficient. Revision means the original proposal was close but not ready, so the graph must preserve continuity while absorbing edits. Substitution means the human has effectively changed the meaning of the pending step and may even be replacing the tool invocation with a human author result. If these branches are collapsed into a generic handled state, the graph loses essential information about how the final action came to be. That weakens auditability and makes debugging much harder. The same distinction appears in the action lifecycle of the Atlas Travel Assistant. A travel request may be approved as drafted, revised to change a destination or limit, or replaced entirely if a human decides the assistant should not book anything at all. Each outcome should leave a different fingerprint and state. Approval should set an approved decision. Revision should produce a new proposal that remains pending. Substitution should record that the human overrode the model and why. The graph is then capable of resuming with full knowledge of what happened, rather than a single undifferentiated interrupt marker. Revision loops, merging edits back into the pending request. Revision is where the graph shows its strength as a state machine rather than a mere prompt wrapper. A human can inspect the proposal, change one or more fields, and return the request to the gate without discarding the surrounding state. That means the system behaves more like collaborative editing than like a binary moderation filter. The human is not required to start over, and the graph does not need to reconstruct the proposal from scratch. It simply merges the edits into the existing object and re-enters the review path. The merge logic matters because revisions are usually incremental. A reviewer may want to change a URL, but leave the query parameters untouched or update only one entry in a parameter dictionary. If the graph replaces the whole object blindly, it can accidentally erase valid fields. That is why the revision node should copy the current proposal, apply only the intended changes, and preserve unmodified values. Partial nested updates are especially important for tool arguments, where a shallow overwrite could delete defaults or remove required context. Incremental state, diff, is safer than destructive reset because it keeps the provenance of the draft intact. The gate function in the earlier code block demonstrates this pattern directly. It copies the current request, then selectively merges the URL and perms field from the human update. That small detail has outsized importance. It means the human can revise the proposal with a narrow edit while the graph carries forward the rest of the object unchanged. The decision field also records that the proposal was revised rather than approved. That makes the loop visible in state, which is useful when debugging repeated revisions or when analyzing why a request took several passes before execution. Revision loops are also where malformed or incomplete responses become operationally visible. If the human response schema is too loose, the update object may omit required fields or include changes that the graph cannot safely merge. If the human edits the wrong field, the system may appear to accept the revision while actually mutating the wrong part of the request. These are the kinds of errors that reveal why schema-constrained responses matter. The graph should not ask the human to just edit the text. It should ask for a structured update that can be merged predictably into the pending object and then routed back through the same approval checkpoint. A committed side effect belongs in exactly one execution node. The separation between proposal and execution is the safety boundary of the pattern. The side effect must not happen during drafting, during review, or during revision. It must happen in exactly one execution node, and only after the graph has recorded that the request was approved. This principle sounds obvious, but it is easy to violate accidentally when a tool wrapper calls an API as soon as the model emits an argument object. In a governed graph, the execution node is the commit point. Everything before it is reversible. Everything after it changes the outside world. The HTTP request node below demonstrates the idea. It does not negotiate with the human, and it does not reinterpret the proposal. It simply reads the approved request from state, performs the external request, and returns a compact summary for downstream nodes. Read the structure first, then trace how each line carries the idea forward. The compactness of the returned result is deliberate. The graph should persist the outcome that later nodes need, not the entire external response by default. A summary such as status code and resolve URL is often enough to inform subsequent routing or user messaging. Storing only the compact result keeps the state focused on durable operational facts instead of duplicating large payloads that do not belong in the control loop. That design also reinforces the safety boundary. The graph carries the decision in a small result summary, while the external system carries the actual effect. This is where the two-track model becomes especially useful. One track is the internal graph state, which accumulates proposal, decision, and summary. The other track is the external world, which changes only when the approved execution node runs. Until then, the side effect remains latent. Approval is the point where the tracks converge. That makes the commit boundary visible in code and in state, which is exactly what production governance needs. Human editing of generated text is the same pattern with a different payload. Approval gates are often introduced using side-effecting tool calls, but the same control pattern applies equally well to generated content. A draft summary, an email response, or a policy explanation can be produced by the model, stored in state, and then paused for human editing before downstream nodes use it. The important idea is that the draft remains a draft until the human overwrites it. The graph does not care whether the payload is an API request or a paragraph of prose. What matters is that the output is reviewable, editable, and resumable. The summary writing node below shows the first half of that pattern. It produces a candidate summary and stores it as state. The editing node then interrupts, asks the human to revise the text, and replaces the stored summary with the revised version. This is not merely a cosmetic editing step. It is a state overwrite that changes what the downstream graph will see. Read the structure first, then trace how each line carries the idea forward. The value of this pattern is not limited to editorial polish. It establishes a general mechanism for human correction of model-produced artifacts. In a travel assistant, the draft might be an itinerary summary. In a support orchestrator, it might be a response draft or a case note. In both cases, the graph treats the human as a state editor, not just as an approver. That is a meaningful distinction because some workflows need correction rather than authorization. The action itself may be harmless, but the generated artifact may still require adjustment before it is fit for downstream use. This pattern also helps draw a line between content correction and action authorization. An approval gate is about whether the system may act outside itself. An editing interrupt is about whether the text produced inside the system is ready to be consumed by another step. They are both human-in-the-loop mechanisms, but they serve different risk profiles. The former controls side effects. The latter controls correctness and presentation. Keeping them distinct prevents the system from turning every review into a policy decision or every policy decision into a content edit. Wrapping arbitrary tools behind one reusable review gate. The most reusable version of this pattern is a generic tool wrapper that applies the same human review contract to any tool, regardless of whether it fetches data, calls an API, or performs some other side effect. That standardization is important because governance becomes brittle when every integration invents its own approval mechanism. A single wrapper can inspect the tool name and arguments, present them to the human with accept, edit, or respond options, and then either invoke the tool, invoke it with edited inputs, or substitute a human response. The policy surface stays the same even as the underlying tools change. Figure 2.10. A reusable wrapper can place any tool behind the same review contract, letting the human accept, edit, or substitute the result before any side effect occurs. The wrapper below makes that idea concrete. It converts non-tool inputs into a tool object when necessary, exposes the tool call as a reviewable action, and routes based on the human's choice. The review payload is not just a string prompt. It is a structured description of the pending action and its arguments. That structure is what lets the reviewer inspect the exact tool invocation that would otherwise happen automatically. Read the structure first, then trace how each line carries the idea forward. This wrapper pattern is powerful because it standardizes governance across heterogeneous integrations. If one tool books travel and another retrieves policy data, both can be placed behind the same accept or edit review contract. That reduces bespoke logic and makes operational behavior easier to reason about. More importantly, it ensures that side effects do not escape the graph simply because a particular tool was added later. The gate is reusable, so the control policy travels with the tool abstraction rather than being duplicated at every call site. The ability to substitute a human response is especially useful when the tool call is being reviewed not merely for correctness, but for appropriateness. Sometimes the best response is not to run the tool at all. In that case, the human can provide the effective result directly, and the graph can continue as though the tool had returned it. That gives the operator a graceful override path without forcing them to mutate the underlying integration or bypass the graph entirely. practical edge cases, and implementation guardrails. The pattern works best when the response schema is tight, the pending proposal is explicit, and state is updated before any routing decision is made. If the schema is too loose, the human response may become ambiguous and the resume logic will have to infer meaning from shape or wording. That is a brittle foundation for governance. If the human edits the wrong field, perhaps because the review payload does not clearly mirror the pending request, the graph may apply an unintended change and then loop back with a corrupted draft. If the state update happens after routing rather than before, the next node may execute with stale or partially applied data. These are not theoretical edge cases. They are the failure modes that appear when approval is implemented as an informal UI flow instead of a control flow primitive. A particularly dangerous failure mode is accidental pre-approval execution. This happens when a tool is invoked before the graph has reached the commit point, often because the tool call was embedded too close to the generation step. In that design, a retry, a parse fallback, or an interrupted human review can still leave the side effect partially triggered. The correct pattern is to keep the proposal in state, interrupt before execution, and route to the side-affecting node only after approval has been explicitly recorded. That way, even if the graph pauses, retries, or resumes later, the execution path remains deterministic. It is also important not to confuse pause semantics with logging semantics. A system can log that a request is pending, annotate a UI, or send an alert without actually stopping execution. Those are useful observability behaviors, but they are not approval gates. An interrupt is stronger. It creates a deliberate pause in the graph and requires a resume input before the next node can run. That is why it belongs in the execution model itself. A logged warning can be ignored. A pause graph cannot proceed without a decision. The final implementation discipline is to keep the proposal, the interrupt payload, and the resume response tightly coupled. The human should see the exact object that will be acted on. The graph should receive a schema-constrained response describing what changed, and the execution node should consume only the approved state. When that discipline holds, approval becomes more than a policy check. It becomes a durable transition in the agent's control flow, one that cleanly separates draft from decision and decision from side effect. Interrupts in a stateful graph are not freezes. They're control flow boundaries that the runtime can cross again on resume. That changes what safety means when a human pauses the workflow. When a node pauses after sending an email or charging a card, the framework sees that as a point it can later resume from. But the outside system already saw the effect. If the node runs again from that checkpoint, the same side effect can repeat. That is the core replay hazard. The framework reconstructs a suspended branch from a checkpoint and continues from where the node was interrupted. If that node mixed an irreversible action with a pause, the same logic can execute again. The code looks correct from a pure Python perspective, but the bug emerges when stateful orchestration meets external side effects. A pure state transformation is safe to repeat because the same input gives the same output. A call to a booking system or payment provider is different. The same input can create a second reservation or charge unless the duplication is built in. The dangerous pattern is interrupting inside the part of the node that already mutated the outside world. Once the effect escapes, the runtime cannot undo it. The figure shows two paths from the same node. On the left, the node modifies internal state and pauses, resuming replays safely. On the right, the node sends a request to an external system before pausing. When it resumes, that external call repeats, causing a duplicate side effect. A travel assistant like Atlas can research and draft a booking request with low risk, but the moment it moves from preparation to commitment, the design must make that boundary explicit. Think of the interrupt as the envelope left on the review desk, not the courier already on the road. Replay-safe orchestration makes the system predictable under pause, review, and resume. Side effects are broader than just database writes, and duplicate side effects cause real damage. This part clarifies what counts as a side effect in an agentic system and explains why duplicates are so expensive. Side effects aren't limited to obvious database writes. In an agentic system, any action that changes the state of an external system or creates an observable event outside the graph should be treated as side effecting. That includes sending messages, creating calendar events, issuing bookings, launching webhooks, posting tickets, making payments, reserving inventory, triggering downstream jobs, or calling third-party APIs that commit work as soon as they are invoked. Even a seemingly harmless action like fetching and storing a quote can become side-effecting if the remote service logs the request, decrements a rate-limited quota, or creates a temporary reservation behind the scenes. The category is broader than many developers expect because the danger is not only durability. It is also irreversibility and observability in other systems. Duplicate side effects are costly because they are usually visible to users long before they are visible in logs. An accidental second booking for a flight, a duplicate hotel reservation, or a repeated payment authorization can create immediate support burden and trust loss. But the damage can be more mundane and still serious. Resending the same email may confuse a customer. Retriggering a webhook can create duplicate downstream tickets. Replaying a write to a CRM can overwrite a corrected value with stale data if a second pass sees a partially changed state. In agent systems, these mistakes are especially frustrating because they arise not from a logic error in the business rule itself, but from the interaction between a good rule and a replayable execution model. The duplication problem is made worse by the fact that many side effects are not obviously visible to the agent at the moment they occur. A tool call may return successfully, yet the confirmation visible to the model can be delayed, partial, or even misleading if the remote system processes work asynchronously. If an interrupt is placed after such a call, the resume node may not know whether the operation completed once, partially, or twice. That uncertainty is exactly why hope the human won't press resume twice is not a design strategy. The workflow should be structured so that the node can be re-entered without creating a second external action, or so that a second entry only repeats a harmless decision step rather than a committed effect. This is also why the safety discussion cannot be reduced to general caution. Side effect safety is a correctness property of the orchestration design. A system that routes approvals, collects edits, and then executes a committed action is not merely more cautious than a direct action system. It is structurally different. The former can make the pause and the commit separable. The latter entangles them and therefore inherits replay risk. That difference is what makes the later sections of this chapter on control flow, handoff, and multi-agent coordination meaningful. Once actions are decomposed into safe stages, the system can branch, pause, and resume without accidental duplication. The core design rule for interrupt-safe nodes is to separate the decision from the action. Put the interrupt on the decision side, where the node gathers candidate state and pauses. The irreversible side effect belongs on the commit side, after approval is embedded in state. This turns a risky mixed-purpose node into two smaller, safer nodes. The node that asks for review should gather or shape the candidate state, expose the relevant draft, and pause. A later node takes the reviewed result and performs the side effect only after approval is already in state. One node is replayable because it does nothing externally visible. The other can be protected with explicit approval semantics. The output of the review step should be a structured state update, not the side effect itself. In an Atlas booking flow, the model drafts a reservation with destination, dates, budget, and preferences. The interrupt presents that draft for editing. Only after those fields are finalized does a separate commit node call the booking tool. This keeps the reviewed object durable in graph state, while the external booking stays one step away. A useful diagnostic question is whether a node contains both a decision and an effect. If the same function computes a course of action, pauses for human input, and then writes to a remote system, it is mixing concerns. The correct structure is to make the pause and the commit independently addressable pieces of the graph, not just move the interrupt earlier in the same function. When review and commit are split, operators can reason about what is still editable and what is already fixed. A paused draft is not the same as a committed reservation. That distinction makes approval screens clearer, audit trails easier to interpret, and prevents the false assumption that a suspended node has merely delayed a final action. The checkpoint preserves the draft. The commit node produces the irreversible side effect only after explicit resume. When a graph branches, multiple branches can stop for review at the same time. Each branch isolates a different kind of human judgment, so the reviewer can edit one field without conflating it with another. Parallel interrupts are a way to structure attention as much as computation. In a branch graph, each pause belongs only to its own branch. One branch may be waiting for a preference edit, while another has already produced a clean, approved value. So instead of thinking of a single global pause state, think of several independent review lanes, each with its own pending question. This distinction matters when branches take different amounts of time to reach their pauses. A fast branch can pause early while a slower branch is still computing, and a system must preserve both without collapsing them into one coarse waiting bucket. The system is not becoming inconsistent just because two branches are waiting. The real inconsistency risk appears when shared state is mutated carelessly while one branch is suspended, or when the review process assumes that all paused branches can be resumed using the same answer. The point of independent pauses is to keep each human decision aligned with the exact piece of state it governs. In the travel example, the reviewer may accept the original destination text but revise the budget text. Those should remain independent choices, not forced into one joint approval, because the semantics of each branch differ. An operator managing several pending pauses is not looking at abstract execution nodes. They're looking at a queue of actionable questions. If the workflow can present each pending interrupt with a clear identity, the human can treat them like separate items in an inbox instead of trying to infer meaning from order alone. That operational clarity is what makes parallel interruption practical, and it sets up the need for stable interrupt IDs. Once multiple review lanes exist, visual order becomes an unreliable way to identify what should be resumed. Once multiple review lanes exist, visual order becomes an unreliable way to identify what should be resumed. Stable interrupt IDs give each pending pause a persistent label, so the operator can confidently pick the right question to answer, regardless of how the queue is displayed. A checkpoint is what makes pause and resume trustworthy. Without it, an interrupt would be just a polite suggestion because the runtime would have no reliable way to restart the exact branch in the exact condition it had before the pause. With it, the graph can pause, a human can respond, and the framework can continue from the same branch local position instead of starting over. A checkpoint is not a long-term memory store or a trace for later analysis. It is a snapshot of execution state that records exactly where each branch was suspended. Without it, the runtime would have no reliable way to restart the branch from the same condition, so the pause would be unreliable. What must be preserved goes beyond the latest values in the state object. The checkpoint needs the execution position of each paused branch, the current machine-readable state for that branch, and the metadata that tells which interrupt is waiting for which response. The state says what the branch knows. The checkpoint says where the branch stopped. In branch graphs, each branch may pause at a different time and resume independently. A branch that paused early must not restart from the top, just because another branch finished later. The checkpoint gives the runtime a durable way to keep these lanes separate, preventing the graph from degenerating into disconnected retries. Checkpointing makes replay a manageable problem. If the framework can reconstruct state exactly, the developer's job is to ensure that any repeated execution before the checkpoint boundary is harmless. The checkpoint does not erase side effects. It only provides a reliable restart point. It preserves the branch, not the world. When multiple pauses can be active at the same time, the operator needs a way to inspect what is waiting. The runtime should expose the set of pending interrupts from the graph state so that a user interface, a CLI, or an orchestration helper can present them clearly. The important thing is not the exact presentation layer, but the information model behind it. The operator needs to see which interrupts are pending, what each one is asking for, and the value currently attached to that pause. Without that inspection step, mapped resumption becomes guesswork, and guesswork is the enemy of a branch-aware workflow. The figure shows a pending interrupt record with 3 fields: a stable interrupt ID, the prompt payload that was presented at pause time, and the current value. The payload is what the agent proposed for human review, not the human response itself. The operator view should preserve that distinction so the reviewer can understand what was proposed before deciding whether to edit, preserve, or override it. In practical terms, the state inspection step produces a list of interrupt records. Each record should include a stable interrupt ID and the payload that was presented at pause time. For the Atlas Assistant, that payload might be the current destination text in one branch and the current budget constraint in another. Those payloads are the prompts for human review, not the human responses themselves. The operator view should also distinguish between no pending interrupts and multiple pending interrupts. When there are none, the workflow can continue without human intervention. When there are several, the interface must make the concurrency explicit rather than hiding it behind a generic approval banner. The human is not approving the whole graph abstractly. They are resolving a set of specific questions. This inspection pattern is also a boundary between the runtime and the person. The graph state tells you what is pending, but it does not itself decide how the human should answer. That decision is still the reviewer's job. What the system can do is present the pause surface in a way that keeps the branch identity, original value, and response mechanism aligned. That alignment is what the helper code in the example is designed to support. This shape is intentionally simple, but the simplicity is deceptive. Each node pauses for a different piece of state, and the graph allows both branches to reach a pause condition independently. The important design choice is that the interrupt is the node's only uncertain act. The branch does not perform a side effect and then ask for review. It asks for review first and only then returns the revised state. Because the graph is compiled with a check pointer, each pause can be resumed later without losing the branch local position. That is what makes the topology safe. If the two nodes had been responsible for committing external changes before pausing, the same branching would become a duplication trap rather than a review mechanism. Figure 2.12 illustrates the replay safe pattern. The node pauses for review first, and only after approval does a separate commit step perform the external action. This separation ensures that replaying the graph does not duplicate side effects. Figure 2.13 shows a branched graph where each interrupt is local to its branch. Multiple review lanes can pause independently without collapsing into one global wait state. This is the concurrency that the operator view must expose. When a workflow pauses in multiple places, the order of those pauses is not a reliable identifier. Branches finish in different orders. User interfaces sort them differently, and reviewers may respond to the easier question first. If resumption relied only on position, responses could get cross-wired whenever display order, execution order, and response order diverge. That is why interrupt IDs must be the authoritative routing key. A stable interrupt ID solves the mailroom problem directly. Each pause branch is an envelope with a label, and the label matters more than the order in which the envelopes arrived. The contents can be read, edited, or preserved, but only if they are returned to the correct address. In mapped resumption, the interrupt ID is that address. It lets the runtime match a human response to the exact pending branch, even when multiple branches are waiting simultaneously or when responses are provided out of order. Without that identifier, the system would rely on fragile positional assumptions that are almost guaranteed to fail in real usage. Using interrupt IDs also protects the system from partial response scenarios. A reviewer may answer one pause now and another later. Another reviewer may respond to a different branch entirely. As long as each answer is keyed by the corresponding interrupt ID, the runtime can merge responses safely without ambiguity. This is especially important in team settings, where the person reviewing the budget field is not necessarily the same person reviewing the destination field. The ID is what keeps the route between human judgment and machine state unambiguous. It is worth emphasizing that the interrupt ID is not just a logging detail. It is part of the control plane. A branch local pause state becomes actionable only when a response can be attached to it precisely. That precision enables both single resume and multi-resume patterns, and it makes the workflow robust against user interface changes, refreshes, and delayed responses. In practice, if an approval screen does not surface these IDs or an equivalent stable mapping, the system is probably leaving too much room for accidental misapplication of human input. It is worth emphasizing that the interrupt ID is not just a logging detail. It is part of the control plane. A branch local pause state becomes actionable only when a response can be attached to it precisely. That precision enables both single resume and multi-resume patterns, and it makes the workflow robust against user interface changes, refreshes, and delayed responses. In practice, if an approval screen does not surface these IDs or an equivalent stable mapping, the system is probably leaving too much room for accidental misapplication of human input. When a workflow has multiple pause branches, resuming it means sending back a map from each interrupt ID to the corrected value. That map preserves the correspondence between what was paused and what the human intends to change. The orchestration helper inspects the current state, finds all pending interrupts, collects human responses for each one, and builds a command with a resume payload key by interrupt ID. This is not a single scalar answer. It is a map that keeps each branch's response separate. If the reviewer leaves an input blank, the helper keeps the original value. That is a deliberate design choice. A blank means keep what is already there, not erase the field. In a travel planning workflow, you might want to change only the budget while leaving the destination text untouched. Preserving the original makes the approval surface a controlled edit, not a destructive form. Human reviewers sometimes need to provide structured data, a JSON object with a date range, a numeric cap, or a typed field override. The helper attempts to parse the input as JSON and falls back to plain text if parsing fails. This respects the shape of the decision. If the pause branch expects a typed edit, the resume payload should carry that typed value, not flatten everything into strings. The result is a resume map that works like a batch of addressed envelopes. Each interrupt ID gets exactly one answer, which can be a primitive value, a preserved original, or a structured JSON edit. The helper is intentionally small because its job is not to implement business logic. It translates operator intent into a control action the graph can safely consume, allowing several pause branches to resume at once without ambiguity. This function shows the whole pattern in code. It gets the state, checks for interrupts, and if there are multiple, prompts the user for each one. The key logic is inside the loop. If the user enters a value, it tries to parse it as JSON and falls back to plain text. If the input is blank, it keeps the original value from the interrupt. The result is a resume map pass to command. This helper makes the workflow's operational shape visible. Pending interrupts are inspectable. Each has a stable identifier. User input can be structured JSON or plain text, and blank responses intentionally preserve the original value. These details are the practical machinery that makes a parallel review lane behave predictably. A mapped command with resume keys lets you restart multiple pause branches in a single action, preserving each branch's identity and avoiding state corruption. When you issue a mapped resume command, the runtime looks at each key in the resume map, finds the corresponding interrupt, and injects the human-provided value into that branch's pause continuation. Each branch resumes from its own save checkpoint, so you get several local resumes executed through one control action, not a single global resume event. Parallel branches are often not symmetric. One branch might receive a text revision while another keeps the original. A third branch might accept a JSON structure with several changed fields, and another remains untouched because the reviewer left it blank. A mapped resume command supports these mixed outcomes without forcing every branch through the same answer shape. That is why a keyed payload is superior to a single scalar response. It can represent the real asymmetry of human judgment. Batch resumption also reduces the risk of partial graph drift. If you resume one pending branch, but leave another waiting with no explicit mapping, the workflow could advance into a mixed state where some branch local decisions have been applied and others remain unresolved. In the worst case, this creates an inconsistent downstream action because one branch's output is consumed while another branch's corresponding field still reflects a stale draft. Mapped resumption avoids that by making the relationship between pending interruptions and their responses explicit at the moment of control transfer. There is a subtle hazard to keep in mind. If a response is stale, the graph may have moved on conceptually even if the checkpoint still exists. The human should always be answering the current pause question, not an older cached interpretation of it. Stable interrupt IDs help here because they tie the response to the exact pause instance, not to a vague memory of what the branch looked like earlier. In concurrent workflows, that precision is what keeps the system from applying a reasonable answer to the wrong moment in the graph. Even with a solid design, real workflows hit predictable problems. Understanding these failure modes and how to guard against them turns a fragile prototype into a dependable system. The most common mistake is placing an interrupt after a side effect has already escaped. When the workflow resumes, that node runs again, causing duplicate records or repeated confirmations. The fix is structural. Move the pause before the effect, or split the node into a review step and a separate commit step. Never rely on human discipline to catch a replayed external call. When multiple branches pause, identifying them by display order is a recipe for disaster. A UI refresh or a delay can reorder the list, and an operator might respond to the wrong branch. The guardrail is simple. Every resume target must be keyed by a stable interrupt ID. The operator sees a friendly label, but the runtime uses the ID as the source of truth. An operator might answer only one pause and forget another, or an approval arrives after the workflow has moved past that checkpoint. The system needs a clear policy for handling stale input. Refuse it, revalidate it, or reissue the pause. The checkpoint tells the runtime where execution left off, but it does not grant permission to apply arbitrary old responses to a newly progressed state. Small ergonomics matter a lot in concurrent human-in-the-loop workflows. A blank response should keep the original value, not delete it. A JSON edit should be parsed as structured data, not stored as an opaque string. When side effects are isolated, checkpoints preserve the pause position, interrupt IDs route responses correctly, and multi-resume maps preserve branch identity. Parallel human review becomes a stable engineering pattern rather than a source of accidental duplication. A multi-agent system is not a single larger prompt with extra personality layers. It is an organizational layer for computation where specialized agents are composed under explicit control flow, shared state, and termination rules. The architectural move is from one agent trying to do everything to a set of agents that each own a narrower responsibility. Capability comes from specialization plus orchestration, not from simply multiplying model invocations. This diagram shows the orchestration layer. Specialized workers each have a distinct role, and the graph defines how work moves between them. Routing, shared state, and termination rules are all explicit, not buried inside a single prompt. If several agents all receive the same prompt and compete for the same work, the result is higher cost, higher latency, and more coordination noise without a corresponding increase in quality. The value emerges when each agent has a distinct role and the graph defines how work moves between those roles. The right mental model is an organizational chart for computation rather than a single conversational thread. A multi-agent workflow answers the same structural questions that a real team must answer. Who decides the next step? Who owns completion? How state moves from one role to another? And what happens when one role finishes, but the overall task is still open? In this supervisor topology, workers contribute local results, but the supervisor alone decides the next step and when execution ends. The routing is centralized, which keeps control explicit and the workflow bounded. Local reasoning happens inside each node, but global policy lives in the graph structure, the routing rules, and the edge definitions that connect nodes together. Once those boundaries are explicit, the workflow remains bounded and debuggable. When they are implicit, the system begins to resemble a loose chat among agents with unclear ownership and weak termination. The topology you choose for a multi-agent system changes behavior because tasks themselves have different shapes of uncertainty. Understanding this connection helps you pick the right pattern for the work at hand. Some tasks are best handled by a single decision maker that inspects the current state and keeps the workflow tightly bounded. Others are naturally layered, with one level making coarse decisions and lower levels handling details. Still others benefit from back-and-forth refinement between peers. The model may look similar, but the coordination semantics are not. The graph decides who speaks next, who owns completion, and how context is transferred. A supervisor architecture centralizes authority, so is easy to reason about and clean to terminate. A hierarchy distributes authority across layers, scaling when one router is no longer enough. A swarm makes responsibility transferable among peers, supporting iterative collaboration when the next move depends on the latest result. These are different answers to the same control authority problem. You can evaluate these patterns through three lenses. Decision authority asks which agent or layer decides what happens next. Scalability asks how far the pattern can grow before the router becomes overloaded. Collaboration style asks whether the workflow is command and response, team and subteam, or reciprocal peer refinement. Bounded linear tasks fit centralized routing. Tasks with subteams suit hierarchy. Work requiring direct alternation between agents calls for swarm behavior. A useful heuristic is to start with the simplest topology that still matches the structure of the work. Use a supervisor first for a clear control surface and predictable termination. Move to hierarchy when a single supervisor becomes overloaded or the problem naturally decomposes into teams. Reach for swarm only when collaboration depends on reciprocal handoffs and the benefits outweigh the extra governance burden. The system should reflect the task, not the aesthetics of the architecture. The supervisor architecture is the most direct way to reason about multi-agent control. It establishes a single locus of decision-making, so every transition can be traced back to one routing decision. A single coordinator reads the shared state, chooses the next worker, and either continues the graph or finishes execution. This gives you specialization without giving up global control, and it keeps the workflow legible because every transition can be traced back to a single routing decision. In the canonical research team example, the supervisor is like an air traffic controller for specialists. It does not search the web, scrape pages, inspect patents, or synthesize the answer itself. Instead, it inspects the current request and dispatches the worker that is most appropriate for the next step. Each worker is narrow, but the supervisor composes them into a coherent workflow. That separation is powerful because the workers can remain opinionated and locally optimized while the orchestration logic stays centralized. The supervisor decides whether the current evidence is sufficient, whether another specialist should contribute, or whether the graph should stop. This keeps prompts and tools for each worker focused on the local job instead of inflating every worker into a miniature generalist. Supervisor routing is also the easiest way to make termination explicit. The coordinator can stop when enough evidence has been gathered, when the final answer is ready, or when another pass through the workers would not add value. Without an explicit owner of completion, a workflow can keep producing partial improvements or dispatching workers long after the task should have ended. The research team graph illustrates the shape of the control flow. A top-level supervisor routes among search, web scraping, alternative search, and patent research. Each worker returns its result to the supervisor, which then chooses the next node or exits. The architectural win is that specialization is combined with controlled routing, so the system can behave like a deliberate workflow instead of an improvisational chat. A supervisor graph needs three things to work reliably: a router that produces structured decisions, worker wrappers that stay focused on their own job, and a clear separation between returning to the supervisor and terminating the whole task. The supervisor must produce a machine-readable next hop decision rather than burying the intent in prose. A typed router schema constrains the model to choose among known options, including a finished state. The graph should not have to interpret natural language to decide whether to continue. It should read an explicit field, map that field to a node, and either route or terminate. The practical pattern is a small router node built around shared state and a type decision object. The state carries the conversation history and any bookkeeping, while the router returns a label like a worker name or a finished signal. The orchestration layer turns that label into a command. The model is not asked to produce reasoning text and hope the runtime infers intent. It produces the control signal the runtime needs. Worker nodes are the other half of the design. A worker wrapper typically invokes a specialized agent on the shared state, extracts the latest result, and returns that result to the supervisor as an update. The wrapper boundary prevents local specialist logic from silently becoming global control logic. The worker does its local job, but the supervisor remains the authority on what happens next. That distinction between returning to the supervisor and ending execution is crucial. Returning means the worker has completed one local contribution, but the overall task is still open. Ending means the coordinator has decided that no further work is necessary. A well-formed supervisor graph keeps those two cases separate in the control flow itself. Each worker transitions back to the supervisor, and the supervisor alone decides whether to continue or terminate. This is the supervisor node factory. The state includes a next field to track the current routing decision. Inside the factory, we define a router type dict with a next field that is a literal union of all worker names plus finish. The supervisor node builds a message list with a system prompt and the conversation history, then calls the LLM with structured output to get a type decision. If the decision is finish, we map it to the Yindi Sentinel. The node returns a command with the target node and an update to the state. The worker node factory creates a React agent for a specific task. The node function invokes that agent on the current state, extracts the last message content, and returns a command that updates the conversation with that content as a human message from the worker. The go-to parameter defaults to supervisor, so the worker always routes back to the supervisor after completing its work. We define a list of worker specifications, each with a name, a list of tools, and a custom prompt. Then we create a dictionary of worker nodes by passing each spec to the factory. Finally, we extract each node by name for use in the graph. We create the supervisor node by calling the factory with the LLM and the list of worker names. This supervisor will route among those four workers and decide when to finish. We build the graph by adding the supervisor and all worker nodes, then adding edges from start to the supervisor and from each worker back to the supervisor. This creates the centralized loop. The supervisor routes to a worker, the worker returns to the supervisor, and the supervisor decides whether to continue or finish. We invoke the graph with a user query about AI agents and LLM agent patents. The stream method yields each node's output as it runs, and we print each step. The recursion limit of 100 ensures the graph can iterate many times if needed. When a single routing layer becomes too coarse to manage the whole problem, we need a hierarchy. The supervisor idea doesn't go away. It expands into multiple layers. Instead of routing only among individual workers, the top-level coordinator routes among entire teams or subgraphs, each with its own internal supervisor and worker set. This shift from managing employees to managing departments is what lets the system scale without making the route unmanageably complex. A hierarchy becomes necessary when one routing layer is too coarse to manage the whole problem. The top-level coordinator routes among entire teams or subgraphs, each with its own internal supervisor and worker set. This shift from managing employees to managing departments is what lets the system scale without making the route unmanageably complex. This nested structure is useful when subtasks have different internal rhythms. A research team may need search, scrape, compare, and validate cycles. A writing team may need outline, draft, revise, and polish cycles. A single router managing all of that directly would become overloaded, and its prompt would accumulate too many concerns. Hierarchy solves this by moving some decisions into lower layers while preserving a higher-level coordinator above them. Hierarchy is more than a diagram with boxes inside boxes. The runtime implication is that each subgraph owns a slice of control flow and returns a result upward when it is done. The upper layer does not micromanage the internal edges of the lower layer. It only chooses which team should receive the task and how the returned result should be interpreted. This is the scaling move from single-agent orchestration to team-of-teams orchestration. The research plus writing example makes the layering concrete. The top-level task is to produce a report, not just gather facts. One team is responsible for research, another for writing. The top supervisor sends the task to the research team first, then routes the resulting material to the writing team, and finally stops once the report has been produced. The orchestration is hierarchical because the outer graph coordinates whole teams, while the inner graphs coordinate the specialists inside those teams. Hierarchical design also preserves autonomy. Each team can change its internal strategy without changing the top-level contract, so long as its inputs and outputs stay consistent. That is a major benefit in production systems. If the research team improves its retrieval strategy or the writing team changes how it drafts and revises, the top-level supervisor does not need to be rewritten. The system grows by inserting a stable boundary between layers rather than by turning the root graph into a monolith. A hierarchical line graph nests subgraphs inside a top graph. The outer supervisor delegates to teams, not to individual workers, which keeps the top-level logic simple even as the system grows. The root supervisor routes to a research team node or a writing team node, and each of those nodes wraps its own internal control flow. The outer graph stays small and readable because it never sees the details inside a team. Strategic flow decides whether the work needs facts or prose, investigation or synthesis. Tactical flow decides which specialist inside the chosen team should act next. This division is especially useful when the final outcome includes a side effect like writing a file, because the top level focuses on the business objective while the lower levels manage the operational sequence. The top supervisor does not need to know whether the research team searches before scraping or whether the writing team drafts before revising. It only needs to know that the research team establishes the evidence base and that the writing team turns that evidence into a finished report. Once the writing team completes its work and writes the file, the outer graph ends cleanly. This code builds the outer graph. The supervisor node is connected to start, and two team nodes are added as regular nodes. Each team node will internally be a compiled subgraph, but from the outer graph's perspective, they are just nodes. The compile call produces the executable super_graph. Here is the task message that drives the whole system. It asks for an 800-word report with an executive summary, recent patents with links, and a final save to disk. The stream call runs the super underscore graph with a recursion limit of 150, printing each step as it executes. The outer graph will route through the research team first, then the writing team, and finally the writing team's write for document tool saves the file. The practical benefit is that the top-level workflow stays understandable even as the underlying system grows. The trade-off is that every boundary adds coordination overhead. The top supervisor must understand team-level results rather than individual worker messages, and each team must maintain a clean contract with the layer above it. This structure is worthwhile when the problem really decomposes into teams, but it is unnecessary complexity when a single supervisor can still manage the job directly. Swarm architecture is the most decentralized of the three patterns. It removes the assumption that a single central coordinator must decide every next step, and instead lets agents transfer active responsibility directly to one another. In this pattern, the collaboration is peer-to-peer, and the flow of control can alternate as the work evolves. This is most useful when the next best actor depends on the latest result, and when iterative back-and-forth refinement is the natural shape of the task. The key concept is handoff. A handoff is not the same as asking for help or ordinary delegation. Delegation may request that another agent contribute while the original agent still owns the workflow. A handoff transfers the floor. The receiving agent becomes active, inherits the shared context, and continues the task from that point. That difference is central to swarm behavior because it allows responsibility to move without breaking conversational continuity. The research writer example is the clearest illustration. The research assistant begins by gathering sources. Once it has enough material, it hands off to the writer assistant, which synthesizes the answer from the collected evidence. If the writer notices that the sources are thin or ambiguous, it can hand back to research for more support. The two agents are not merely exchanging messages. They are transferring active responsibility while preserving the state of the task. That reciprocal motion can be more expressive than a strict supervisor graph when the work converges through iteration. Research may surface a missing citation that changes what writing can safely claim. Writing may expose a gap that sends the task back to research. A centralized router can still manage such a loop, but the swarm pattern lets the agents closest to the issue pass control directly. That can reduce unnecessary central churn when the work genuinely alternates between discovery and synthesis. The trade-off is that peer-to-peer control is harder to govern. There are more chances for oscillation, more risk of unclear ownership, and more ways for a workflow to keep handing responsibility back and forth without converging. Swarm design is therefore best when collaboration style is the main requirement and when the team can tolerate a more complex control structure. It is flexible, but it is not automatically easier to reason about than a supervisor. In many systems, the simplicity of central routing is the better production choice. A line graph swarm uses handoff tools to transfer control between agents. A default active agent to start the conversation and alternating turns to keep the work moving without losing context. Handoff tools are the mechanism that moves control from one agent to another. They're not ordinary tools that return data. Those leave the caller in charge. A handoff changes who owns the conversation next, while the shared state stays intact so the next agent can pick up from the current context. The default active agent gives the swarm a starting point. When a user request arrives, one agent begins in charge, typically the one best suited for the first task. In a research writer swarm, the research assistant starts by default because the work begins with gathering evidence. That choice reduces unnecessary bouncing. Alternation comes from the handoff contract itself. The research agent gathers sources and passes control to the writer. The writer synthesizes the answer and, if more evidence is needed, hands back. Each handoff transfers active responsibility to a peer, so the two agents collaborate without losing continuity. The shared messages stay in the graph, but the floor moves. We define two handoff tools. Each one names the target agent and describes when to use it. The research assistant uses to_writer to hand off to the writer, and the writer uses to_research to send a task back for more sources. Each agent is created with create_react_agent. The research assistant gets the web tools plus the handoff to the writer. The writer only gets the handoff back to research. It does not need its own search tools. The prompts tell each agent when to hand off. The swarm is assembled with create_swarm, listing both agents and setting the research assistant as the default active agent. Then compile prepares the graph for execution. We send a user request asking about Swiss fintech licensing. The swarm processes it, and we stream the output chunk by chunk. Each chunk shows which agent is active and what it produces. The key insight is that a handoff tool changes the active agent, not just the message content. A regular tool call returns data but leaves the caller in charge. A handoff transfers authority to a different agent while preserving the shared context. That is what makes alternating turns work without losing continuity. Routing, delegation, and handoff sound similar, but each one controls how work moves through a multi-agent system in a distinct way. Keeping them straight is essential for designing reliable agent graphs. Routing is a graph-level decision. The system looks at the current state and chooses which node should execute next. Delegation means assigning a piece of work to another agent, but the delegating agent may still remain active. Handoff is different. It transfers active responsibility, so the receiving agent becomes the current owner of the task. If you blur these, it becomes hard to reason about who owns the task when it terminates or how state moves through the system. A supervisor topology is primarily about routing. The coordinator evaluates shared state and picks the next worker or ends execution. A hierarchy extends at routing across layers. The top supervisor routes to teams, and each team routes internally. A swarm makes handoff central because the active agent itself can decide to transfer responsibility to a peer. The common thread is movement through the graph, but the control semantics are not the same. It is important not to treat every tool call as a handoff. When an agent calls a search tool, the same agent remains active after the result returns. Asking another worker to help is not the same as transferring control. Handoff is about responsibility transfer, not just data transfer. That is why handoff tools need to be modeled explicitly rather than folded into ordinary utility calls. They affect the control structure of the graph, not just the contents of the message buffer. Once these terms stay separate, the design becomes much easier to reason about. Routing tells you where the workflow goes next. Delegation tells you how work is apportioned. Handoff tells you when the active role changes. Multi-agent systems become reliable when each of those decisions is represented deliberately in the graph rather than assumed implicitly in conversational text. Multi-agent workflows become real when you can see them execute, not just when you describe them. This part covers 3 runtime concerns that turn a diagram into a running system. How the graph is assembled into a state machine, how streaming exposes each transition, and why recursion limits are first-class architectural constraint. Graph assembly is the moment the abstract topology becomes a runnable state machine. Nodes are registered, edges are drawn, and the graph is compiled. A compiled graph is not a loose conversation among agents. It is an executable control flow, and the runtime enforces the legal transition step by step. Streaming execution is useful because it exposes the orchestration path while the graph runs. Instead of waiting for a final response, you can observe each transition as it happens. Supervisor to worker, worker back to supervisor, supervisor to another worker, or one peer handing off to another. That visibility is one of the best debugging tools for multi-agent design because it shows where the workflow spends time, where it bounces, and whether the control logic is actually converging on an end state. Recursion limits are first-class concerns as soon as more than one node can hand control back and forth. A supervisor or a swarm can loop if the termination logic is too weak or if 2 nodes keep deferring to each other. A recursion limit is not just a defensive programming detail. It is a practical bound on runaway coordination cost. If a research node keeps handing work back to writing and writing keeps returning to research, the limit forces the run to stop before time, and tokens are wasted indefinitely. The broader lesson is that observability and bounding are part of the architecture itself. A multi-agent system is not really complete until it can be compiled, streamed, and stopped cleanly. Graph edges, step-by-step execution traces, and explicit recursion limits are the runtime expression of the topology. If you cannot inspect the transitions or cap the loop, the coordination design is not yet production ready. The topology you choose for a multi-agent system directly shapes how the work gets done, how easy it is to debug, and how the system behaves under load. This part walks through the trade-offs among supervisor, hierarchy, and swarm so you can match the structure to the task. A supervisor gives you the clearest control surface and the simplest termination semantics, so it is a natural starting point. If the work decomposes into teams or phases, hierarchy distributes decisions across layers. For iterative, reciprocal work, where agents hand responsibility back and forth, a swarm can be more flexible. The guiding principle is to match the topology to the behavior of the task, not to how novel the pattern looks. A compact comparison makes the trade-off clearer. Centralized supervision concentrates decision authority, so it is straightforward to govern and usually easiest to debug, but it can become a bottleneck when a workflow branches heavily. Hierarchical coordination scales better for complex jobs because it distributes decisions across layers, but introduces more boundaries and more overhead. Swarm coordination is the most flexible for peer refinement, but it is also the hardest to govern and the easiest to let drift into oscillation or unclear ownership. More flexibility usually means more coordination cost. That cost is not just conceptual. It shows up as latency, token usage, and contention over who should act next. As the number of agents increases, the system spends more time on coordination and less on direct task progress unless the structure is carefully designed. A supervisor can over-serialize work. A hierarchy can create interface friction between teams. A swarm can consume time passing responsibility back and forth. The topology choice, therefore, has a direct effect on runtime efficiency as well as on maintainability. The failure modes are also topology-specific. Supervisors can become overly conservative and route too much work through one central bottleneck. Hierarchies can suffer from dead ends when a subgraph finishes locally but fails to hand back a clear result. Swarms can oscillate, with agents repeatedly handing control back and forth without converging. Unclear ownership is especially dangerous because it makes the workflow hard to terminate cleanly. These problems are not abstract. They are direct consequences of how the graph represents authority and transfer of responsibility. A practical selection rule follows from those trade-offs. Choose supervisor first for a new multi-agent workflow because it gives you the most direct control and the least ambiguity. Add hierarchy when a single supervisor can no longer manage the internal complexity or when distinct teams need their own local loops. Use swarm when the central requirement is reciprocal peer collaboration and the work genuinely improves through alternating responsibility transfer. In short, prefer the simplest topology that faithfully matches the task, and introduce more structure only when the work demands it. An agent's capability does not live solely inside the model. The architecture around the model determines what it can do, how often it can revise, when it must stop, and whether its decisions are reversible. A stronger model can improve judgment, language quality, and tool selection, but the architecture decides the difference between a one-shot completion, a controlled sequence of transitions, and a distributed system with delegated responsibility. The same model can behave like a careful analyst, a brittle text generator, or a bounded operator, depending on the control structure wrapped around it. This figure shows four different control structures wrapped around the same model. On the left, a simple prompt produces a single output. A workflow adds sequential steps. A loop allows the model to iterate and revise. And a multi-agent system distributes responsibility across specialized actors. The model itself stays the same, but the behavior changes dramatically. If a system improves after adding a planning loop, a tool call, or a review gate, the improvement did not come from prompt wording alone. It came from giving the model a shape in which to operate. A fluent speaker without grammar can still produce words, but not necessarily coherent action. An LLM without a control structure may generate plausible outputs while remaining unable to reliably decompose work, inspect outcomes, or recover from mistakes. This chapter has moved from structured reasoning into loops, interrupts, and coordination. Kant gives reasoning a more deliberate internal shape. Tot turns deliberation into branching search. React couples reasoning with execution so the model can observe the consequences of its own actions. Interrupts and approvals make autonomy conditional rather than absolute. The common thread is more deliberate control over time. Think of architecture as the terrain and the model as the traveler. The traveler's skill matters, but the available routes, the difficulty of the path, the points where you can stop and look around, and the possibility of handing the map to another guide are all properties of the terrain. If you want a system that can safely navigate a bounded but messy task, you must shape the terrain first. Prompt quality can sharpen the traveler's judgment, but it cannot replace roads, checkpoints, and route selection. Control flow transforms a single prediction into a sequence of decisions. A one-shot completion must solve the entire problem in one move, which becomes fragile when the task requires decomposition, verification, or access to external state. A multi-step loop separates those concerns. One pass plans, another acts, a subsequent pass observes, and the next revises. The capability gain comes from giving the model multiple opportunities to narrow uncertainty and correct mistakes before the final commitment. A one-shot completion is constrained to solve the entire problem in one move. The model must simultaneously interpret the request, search for a solution, and emit a final answer. That works for small tasks, but becomes fragile when the task requires decomposition, verification, or access to external state. A multi-step loop lets the system separate those concerns. One pass can plan, another can act, a subsequent pass can observe, and the next can revise. The capability gain comes from giving the model multiple opportunities to narrow uncertainty and correct mistakes before the final commitment. Without state, each turn is a fresh guess detached from the previous one. With state, the system can accumulate commitments, failed branches, user preferences, and partial results in machine-readable form. That changes the model's effective search space. It can preserve promising directions, abandon unproductive ones, and enforce rules about what is still pending. Control flow acts like a scaffold around inference, allowing the agent to climb higher than a single prompt response exchange would permit. In a one-shot setup, an early misconception tends to contaminate the entire answer. In an iterative setup, each observation can constrain subsequent actions. That is especially important for tasks with external side effects, such as search, booking, writing, or ticket triage. The system is no longer just generating text about the task. It is moving through the task itself. Every transition becomes an opportunity to validate assumptions, and every validated step reduces the remaining uncertainty. Control flow should be treated as a source of capability rather than a mere engineering detail. The Atlas Travel Assistant can answer a simple question in one shot, but when the task becomes research options, compare constraints, request approval, and book, the control structure becomes the real product. The model may still be the same, but the system now has a way to represent pending decisions, branch when the itinerary is unclear, and pause before sensitive actions. That transformation is not just safer. It is more capable, because the system can now accomplish tasks whose solution requires time, revisability, and interaction with the environment. Structured reasoning patterns transform a static model completion into a controllable agentic process. Chain of thought is the first step in that bridge because it encourages decomposition before commitment. The goal is not simply to produce longer explanations. By separating hidden intermediate reasoning from the final answer, the model avoids collapsing distinct subproblems into a single vague judgment. This improves the odds that dependencies are noticed, alternatives are compared, and complex tasks are handled step by step. Tree of Thoughts pushes further by making branching explicit. Instead of a linear march, the model explores, scores, and prunes candidate paths. This matters when multiple plausible lines of attack exist and no single deterministic path guarantees the solution. The conceptual advance is algorithmic power, not just prompt styling. React marks the transition from reasoning in isolation to reasoning in contact with the world. Instead of solving the problem entirely inside the model, it invokes a tool, inspects the result, and updates its next move. This loop converts uncertainty into evidence. The model stops guessing and asks the environment. Each pattern expands the model's effective horizon. Chain of thought improves local decomposition. Tree of thoughts expands the search frontier. React turns that search into action in the loop. Together, they explain why a system can appear much more capable even with the same underlying model. The architecture allows it to think, branch, observe, and revise before finalizing behavior. Once you understand the patterns, the real question is not which one is most advanced, but which one fits the shape of your task. This section gives you a practical way to choose. A workflow is the right choice when the path is known in advance, the transitions are stable, and predictability is the main requirement. If the task can be expressed as a sequence of fixed or semi-fixed steps, a workflow gives you clarity, testability, and auditability. The model may still assist within a step, but the control logic remains external and explicit. This is often the best option when the business process is mature, the acceptable action space is narrow, or compliance demands a traceable execution path. A single agent loop becomes attractive when the path is not known up front, but the task still belongs to one cognitive thread. The defining feature here is iteration. The model can inspect output, decide whether it is sufficient, call tools again, refine a plan, or recover from an error. This is the middle ground between rigid orchestration and distributed cooperation. Use it when the same agent needs to search, verify, and adapt while remaining the only decision-maker in charge of the task. Atlas Travel Assistant fits this pattern well when it is comparing options, checking constraints, and refining a proposed itinerary before escalating for approval. A multi-agent system makes sense when the problem is decomposable into specialized roles whose separation is itself valuable. If research, drafting, verification, and policy checking benefit from distinct responsibilities, then multiple agents can outperform a monolithic loop, not because they are magical, but because they make coordination explicit. The benefit may come from parallelism, but it often comes just as much from specialization and accountability. Different subagents can hold different prompts, tools, constraints, and success criteria, which reduces the cognitive burden on any single model invocation. That said, the system also inherits new coordination costs: routing, synchronization, conflict resolution, and the possibility of one agent amplifying another's mistakes. The cleanest way to choose among these patterns is to ask what kind of uncertainty dominates the task. If the uncertainty is low and the path is known, a workflow is enough. If the uncertainty is medium and the task requires iterative refinement, a single agent loop is often the right balance. If the uncertainty is distributed across different specialties, or if the task materially benefits from parallel work or independent review, then a multi-agent system begins to justify its overhead. This is why architecture should be chosen from task shape, not from fashion. More autonomy is not inherently better. It is only better when the structure of the problem makes autonomy productive. Another useful filter is reversibility. When mistakes are cheap and easy to roll back, you can afford more autonomous exploration. When mistakes are expensive, a more constrained workflow or a gated loop is usually wiser. A travel agent that merely recommends hotels can explore freely. A travel agent that can reserve non-refundable rooms should not. The same distinction applies in support, finance, operations, and code execution. The more expensive the error, the more you should prefer explicit control over free-form agency. Oversight is not an afterthought bolted onto an architecture. It is a primary design axis that defines how much autonomy an agent actually has. Human-in-the-loop control is baked into the architecture itself. An interrupt pauses execution at a meaningful boundary. An approval gate requires a person to authorize a sensitive continuation. A review step lets a human inspect or edit state without taking over the whole process. These are not safety decorations. They are deliberate design choices that determine where the agent proceeds on its own and where it must defer. The crucial distinction is between the kinds of intervention that are allowed. Some interrupts are purely supervisory, letting a human read what the system has prepared. Some are editorial, allowing a person to modify a draft or adjust parameters before resumption. Some are validating, where the human confirms that a generated action matches intent or policy. Others are true approval gates, where execution may not continue until authorization is explicitly given. Treating all of these as the same would blur important operational differences. Oversight also changes the economics of error. It adds latency and human effort, but it reduces blast radius. That trade-off is often rational even when the system is otherwise capable of more autonomy. A booking step, a destructive write, a policy-sensitive reply, or a high-cost external action may be perfectly reachable by the model, yet still require a checkpoint because the cost of an error dwarfs the cost of review. The smartest architecture is often the one that knows where not to be clever. Oversights should be placed with intention, not sprinkled everywhere. Too many pauses can make a system unusable, but too few can make it reckless. The design problem is to identify where a human adds the most value, catching uncertainty, confirming intent, or approving side effects. That is a better framing than asking whether the system is autonomous in some absolute sense. In production, autonomy is rarely binary. It is negotiated at each transition. Multi-agent systems are often introduced to scale intelligence, but their real value is coordination under specialization. The key question is how to delegate work without surrendering accountability. This section compares three architectures that answer that question in different ways: supervisor, hierarchy, and swarm. The supervisor architecture keeps a single accountable center. A central controller decides what work needs to happen, dispatches tasks to specialized agents, and then receives results for synthesis. The supervisor does not need to perform every subtask itself, but it preserves a clear point where decisions, priorities, and stop conditions are managed. This is especially useful when the task can be decomposed, but you still want a single place to control the process. Hierarchical architecture extends that idea by letting delegation become recursive. A top-level manager assigns work to a mid-level coordinator, which in turn distributes sub-work to narrower specialists. This resembles a project organization more than a flat pipeline. Each level has a bounded role, and handoffs define where one unit's responsibility ends and another begins. The cost is that coordination overhead can accumulate and state can drift between levels if the hierarchy is too deep. The distinction between supervisor and hierarchy is not about whether there is control, but about how control is distributed. A supervisor keeps the center visible and the structure relatively flat. A hierarchy spreads control across layers while preserving authority relationships. Both are answers to the same question. How do you delegate work without surrendering accountability? In a support system, a supervisor might route a request to research and drafting specialists and then decide on escalation. In a deeper hierarchy, an intake layer classifies the issue, a mid-layer retrieves policy, and a lower layer drafts the response. Swarm coordination occupies a different place in the design space. It emphasizes peer-to-peer interaction, distributed contribution, and sometimes dynamic role assignment. That can be useful when the work is highly exploratory or when many partial perspectives need to converge. But swarm systems are usually harder to control because no single agent owns the entire trajectory. They often require stricter governance and stronger convergence criteria to avoid drift. In production, swarm should be a deliberate choice, not a default enthusiasm. It is most justified when the value of distributed exploration outweighs the cost of coordination. All the patterns in this chapter, despite their different names, rest on the same few mechanical ideas. Understanding these shared primitives makes the patterns easier to learn and compare. Every pattern depends on explicit state, whether that's a planning agenda, a pending decision, a search tree branch, or a record of which agent owns which subtask. They all depend on transitions because nothing useful happens until the system moves from one state to another under some rule. They all depend on traceability because without a record of decisions, tool calls, and handoffs, neither debugging nor governance is reliable. And they all depend on bounded autonomy because an agent that can act without constraint is not necessarily more useful. It is often merely more dangerous. Tool mediation is another shared primitive. A tool call is a controlled interface between inference and execution. Whether the system is a single-agent loop or a multi-agent team, the model does not directly touch the world. It acts through bounded tools. That separation is what makes the architecture inspectable. It also makes review possible, because the system can present a proposed action as structured state rather than as an unstructured intention buried in prose. Once a tool is mediated by state and policy, it becomes easier to gate, replay, modify, or hand off. Handoffs deserve special attention because they reveal the continuity between single-agent and multi-agent systems. A handoff is not just delegation in the conversational sense. It is a transfer of responsibility embedded in execution state. One component stops being the owner of a task, and another takes over with enough context to continue. That is why handoff is central to both coordination and governance. It is the moment when a task changes hands while the system preserves enough structure to keep moving. In a well-designed system, the handoff is visible, explicit, and auditable. Seen this way, the chapter's patterns are not isolated inventions. They are variations on controlled execution. A workflow constrains transitions in advance. A loop permits iterative self-correction. A multi-agent system distributes work while retaining structured ownership. Interrupts and approvals insert governance into the same flow. You should now be able to recognize these as different ways of composing state, transitions, and authority around the model, rather than as unrelated architectural fashions. Choosing the right control pattern for an agent system starts with two things: the shape of the task and the level of risk involved. This framework helps you match architecture to the work itself, so you avoid over-engineering. If the task path is stable, the decision criteria are clear, and the outcome needs to be easy to audit, a workflow is the natural default. If the system needs to investigate or search over possibilities while staying a single decision-making unit, a single-agent loop fits better. And if the work breaks into specialized subproblems that benefit from separate roles or parallel review, a multi-agent design becomes attractive. This sequence resists over-engineering. You start with the smallest control structure that can reliably express the task. This figure shows the decision flow. On one axis, you have uncertainty and reversibility, how much the task might change, and how hard it is to undo a mistake. On the other axis, you have specialization needs. The goal is to pick the smallest architecture that still fits all three constraints. Risk is what decides how much autonomy the architecture should expose. Low-risk tasks can tolerate broad exploration because errors are cheap to fix. Medium-risk tasks benefit from bounded loops that can self-correct before committing. High-risk tasks should include interruptions, approvals, or explicit handoffs before any side effect becomes permanent. The harder it is to undo a mistake, the more structured the control flow should be. Collaboration need is the third major axis. If the work benefits from one coherent reasoning thread, a single-agent loop keeps coordination overhead low. If the work is fundamentally cross-functional, specialization can outperform monolithic reasoning. Research, drafting, policy checking, and final approval are not the same job, even if they are all language tasks. A multi-agent system can give each role a different prompt, tool set, or decision boundary. A good test of whether a pattern is justified is whether the added structure reduces ambiguity more than it adds overhead. If a new control layer creates clearer ownership, better checkpoints, and better error containment, it is doing useful work. If it only adds orchestration complexity, it is likely premature. Every new degree of freedom should earn its place by improving correctness, safety, or the quality of decomposition. The same framework also helps with language. If you can explain the design in one sentence, the path is known, the task needs iteration, or the work is specialized and distributed, you're probably close to the right abstraction. If you need a long story to justify why many agents exist, you may be disguising avoidable complexity. Simplicity is not an aesthetic preference. It is a risk control strategy. Adding more autonomy is tempting because it makes a system look more capable. But the real question is whether it makes the system more reliable and easier to understand, not just more impressive. When coordination overhead starts to outweigh the benefits of delegation, the architecture gets heavier without getting better. More agents can mean more latency, more chances for disagreement, and more surfaces where the system can drift off course. If the environment is predictable and the process is already well-defined, a simple workflow is often the better engineering choice. Adding a deliberative loop just creates extra branches that need testing and monitoring. And a multi-agent system is rarely justified if the subtasks aren't genuinely separable. If every specialist has to reconstruct the same shared context, you're paying coordination costs for little gain. A system might seem more capable because it produces longer plans or more internal debate, but if those additions don't reduce error or improve task completion, they're decorative. In production, decorative autonomy is a liability. It looks advanced, but obscures responsibility and makes failures harder to diagnose. Reversibility should stay central in design discussions. If a mistake is costly and recovery is difficult, the system should be conservative about how much freedom it exercises. The right answer might be a workflow with a single approval gate, not a richer agentic loop. Restraint is not a lack of sophistication. In many production settings, it is the sophistication. Architecture is the foundation for everything else in the agent stack. The control pattern you choose determines what you need to observe, store, retry, approve, and delegate. Production hardening, observability, evaluation, memory, cost control, and security all inherit their shape from that choice. A workflow is measured and guarded differently from a loop, and a loop is monitored differently from a multi-agent team. The orchestration pattern defines what counts as a meaningful unit to inspect, retry, or approve. Later concerns are not independent add-ons. They're shaped by the architecture from start. These distinctions matter because they determine how you persist, deploy, test, and secure the system. If the architecture is unclear, every downstream concern becomes harder to reason about. If it is explicit, production controls attach to specific transitions, evaluation targets specific behaviors, and memory stays separate from short-lived execution state. Once an agent can think in steps, the question becomes how to harden those steps into reliable software. Once it can hand off work, the question becomes whether those handoffs improve quality or add latency. Once it can pause for approval, the question becomes how to keep the pause useful. Architecture does not end those questions, it organizes them. Prompt quality matters, but it is only one ingredient. The control structure determines whether the model can revise itself, branch, defer, delegate, or act safely under uncertainty. The model supplies the mind, but architecture supplies the rules of action.